Development in Bioenergy Research. We shall start this session with presentation by two scholars from IIT Kharagpur. The first speaker is Mr. Shubhajit Banerjee, who is a PhD scholar from P.K. Sinha Center for Bioenergy and Renewables, IIT Kharagpur. He will talk on studies on delignification of sugarcane bagasse as part of a large-scale study to analyze and valorize different lignocellulose towards 2G biofuel production, an enzymatic venture. Mr. Banerjee, please.
Thank you. I'm going to share the content now. Can everybody see the presentation and hear my voice?
Yes, we can see it and hear you too.
Okay. Thank you. So, my name is Subodhi Banerjee. I am a second year JRF working under the supervision of Professor Rintu Banerjee, Head Department of Agriculture, and Professor Tapas Kumar Bandyopadhyay of Metallurgy and Material Science Department. I am registered at IIT Kharagpur through Advanced Technology Development Center, and I will be presenting uh, some portion of review literature and some portion of the work that I have done on the basis of delignification strategies and of sugarcane bagasse, as well as what others can undertake as delignification strategies to pre-treat different types of biomass that are presently used for biofuel production, specifically 2G biofuel production. So, as discussed earlier by Mr. Romit Mitra, there is a need for alternative fuel development and production, as well as these fuels are not gifted by nature. These fuels are manufactured by humans. So we must also know the strategy behind why we are doing this. Of course, the fossil fuels are depleting at an alarming rate annually, and energy demand is increasing day by day. As also, there is a huge increase in the greenhouse gas emission. But for developing countries like us in India, there are more things at stake. Our whole crude oil deposits, we have very few crude oil deposits and have to be heavily dependent on foreign nations for the energy supply. And whatever the new renewable energies are coming, like solar energy or any kind of wind energy, during transportation, the alternative to liquid biofuel is very limited. Liquid biofuel is the optimum fuel that can be used for large scale transportation throughout the country. And also, to develop liquid biofuel infrastructure, there is also an economic development angle that we must consider, both in our country and in other developing countries as well, because this will entertain a huge number of job generations for sustaining in agriculture as also valorizing agriculture. Otherwise, you all know that the agriculture wastes are in the field and they burn the agriculture waste, which result in immense fog in the northern parts of India as well as in other regions of the country and world. So if you can valorize those waste in the form of fuel, that would be a great help, not only in reducing the fuel crisis as also for the environment. So here we can see that day by day the energy unit is the crisis or the demand for energy is increasing year by year, and in 2040 it will be 815 quadrillion units of energy. And of that total energy now, what we find out that oil is contributing to 38% of the total fuels, natural gas to about 21%, and coal to 21%. Nuclear is very less due to the security threats that they pose, and renewable in 18%. Among that bioenergy renewable of 14% is mostly by using of solid biofuels like burning of agricultural waste and so on. So that though the government has mandated that rice straw pellets and other excess agricultural pellets can be used in thermal reactors, still they pose the same problem of mass burning and mass carbon emissions. For that reason, conversion of those agricultural waste to bioenergy or liquid biofuel can be considered. So in the world energy consumption, the increase per year of renewable energy is 2.6%, nuclear energy is 2.3%, natural gas is 1.9%, and coal is decreasing. So why is coal decreasing? Because coal mainly provides thermal nuclear powers, whereas the renewable energy has a great deal to provide as blended material in liquid biofuels. For that reason, we consider liquid biofuel generation through through lignocellulose a very important aspect to be researched. So the biofuel is a renewable energy source that is unlike other crude oil sources or like petroleum, coal and fossil fuels. They are extracted from plants and crops, as you all know, and biofuel can be used for transportation, power and heat generations. So commonly used liquid biofuels are bioethanol, which is being widely used. And the reason for bioethanol being widely used is that we have known ethanol generation for not only centuries but for like thousands of years. We have known ethanol generation, and to harness the power of that ethanol generation in powering up the machines, the cars, has been a very important factor for the use of renewable energy, and Brazil can be considered as one of the topmost country who has changed the perspective of biofuel generation in case of ethanol generation through sugar canes as one of the main component of fuel replacing fossil fuels. So we can know the classification of biofuels, that the primary biofuels is wood chips and wood pellets, and secondary biofuels that are processed from those primary biofuels are ethanol, butanol, biodiesels, solid biofuels that are charcoal, and gaseous biofuels as biomethane and biohydrogen. So in case of also primary biofuels, in when you use primary biofuels in large scale burners, like nowadays the business of bricks, biomass bricks for furnaces is increasing, that too requires a certain level of pre-treatment. So why pre-treatment? Because they are almost all hardwood. They have to be compressed, and in softwood also, for optimal burning, the fibers of the woods has to be let loose so that optimal burning can be achieved in furnaces. So pre-treatment has become a very important step in utilization of biomass for second generation biofuel. So what are the advantages of biofuel? They are renewable. Of course they are renewable. They reduce greenhouse gases emission. They have very little SO2, NO2 emissions. They are provide economic security to a certain extent because we don't have to depend on other countries who have those natural resources to give that to us in exchange for a price. There are also availability of biofuels. As we have availability of biomass, we have availability of biofuels, and of course the environmental impact in case of reduction of greenhouse gas emission as well as reduction of use of crude oil deposit, and also saving the crude oil deposits for those industries that definitely require them. But these also comes with a certain disadvantage also, like there is high cost of production, there is regional suitability, like every region cannot possess the same substrate for biofuel generation. Like Brazil grows mostly sugarcane, so they use sugarcane. US grows mostly corn, they use corn. But here in case of US, they use corn to a certain amount of extent that at some portion of the time they had to import corn from Mexico. And for that there was a crisis of corn as food in Mexico, and that rises to the food security and the impacted food versus fuel controversy. And also, if we are now going to cultivate special crops for biofuel generation, then we will face a land use issue. Like if you are able to cultivate algae for biofuel generation, you have to have specific ratio ponds or lands to cultivate algae, which develop some policy issues. So that things we should keep in mind. Now in my work, I took sugarcane bagasse, which is a combination of the cellulose, hemicellulose and lignin polymers. After that, a pre-treatment strategy. Here in case an enzymatic pre-treatment strategy with degradation of lignin molecules. There are like lignin molecules which can precipitate. They are like lignin derived degraded molecules, and also the same cellulose and hemicellulose complex, and also hemicellulose which can further move on to saccharification. So the current pre-treatment methods now I am going to discuss. So for starting of current pre-treatment methods, the first one that comes to mind is a physical pre-treatment method. So why physical pre-treatment method? This is a very vital method because for all other methods, in many methods, physical pre-treatment is the basis that can be used like a pre-treatment method. It decreases the crystallinity, it decreases decreases the degree of polymerization of the cellulose molecules, and also it increases the surface area and the size of pores so that more and more enzyme can act on those substrates during hydrolysis. So different types of physical processes are there, such as ball milling, two-roll milling, hammer milling, colloid milling, such and such. And also there are some other pre-treatment processes such as irradiation methods. Why irradiation methods? Just the way like gamma rays and other electron beams disrupt our cells and cause cancers, this same strategy can be used to disrupt the biomass and to improve the hydrolyzing property, or to improve so that the biomass can be more and more hydrolyzed by the enzyme, that the biodegradation of lignocellulosic waste can be achieved. Reduction in particle size is one of the most important aspects of physical pre-treatment because it makes it easier to handle, and as I said, it comes as a pre-treatment method. So in physical treatment method, the size often is reduced to 0.2 to 2 millimeter after milling, and this mechanical pre-treatment method is carried out as a processing step involved with acid and enzyme pre-treatment to achieve the desired particle size. And also there is this irradiation with gamma rays and electron beams, as also a very recent development of ionic liquid usage with a microwave is also a very important pre-treatment method that is being used nowadays. The combination of the radiation and other methods such as acid pre-treatment or alkali pre-treatment accelerate enzymatic hydrolysis. So these are all extension portion of the physical pre-treatment. So there are also the physico-chemical pre-treatment, and what comes in that is the steam pre-treatment. So what is the steam pre-treatment? Steam is used which is of very high temperature along with pressure, and the biomass is bombarded with the steam. This has dual effect, it's like acts as an autoclave. It kills other organisms that are present in the biomass, as also it breaks down the biomass. There's hemicellulose being a prominent fraction of the carbohydrate during pre-treatment, and lignin is also transformed in that high temperature. Cellulose becomes more easily accessible during steam pre-treatment for enzymatic hydrolysis later. Also during this high pressure and steam, acetic acid generated. These acetic acids further catalyze the hemicellulose and lignin bonds and release the lignin, and it becomes more and more easier for enzymatic hydrolysis. So there are some certain disadvantage of steam pre-treatment, like sometimes the steam doesn't reach every nook and corner of the carbohydrate matrix, and thus sometimes a portion of the biomass when in large quantity is not pre-treated and makes it less digestible for the generation of fermented. And also in that high temperature, certain fermentation inhibitors are generated. I will come to that later. So, and for this reason, like a washing is done to reduce those inhibitors, and for that a large portion of soluble sugar is misplaced that could have been used to generate liquid biofuel. So what is liquid hot water pretreatment? Liquid hot water pretreatment is just like steam pretreatment, but while using water. So it has more accessibility, the water has more accessibility to the biomass. It forms all the like linkages, the acetic acid and everything. It has been shown to be more effective than steam pretreatment, but it also uses a very large amount of water, which is a precious commodity. Now we come to the chemical pretreatment. Like there is ammonia fiber explosion or ammonia recycle perforation. What happens in that? Like ammonia or liquid ammonia is used as an alkaline pretreatment media in ambient temperature present of pressure. The ammonia comes in contact with the biomass, degrades the biomass and evaporates. And it is again recollected and repercolated through the beds for pretreatment. Like in ammonia pretreatment, like 1:1 or 1:2 ratio of ammonia to dry mass is used, and the pressures, and when the pressure is removed, the ammonia vaporizes and the biomass is obtained in a slurry or sludge form in a pretreatment manner. So the chemical effects of ammonia under pressure causes the cellulosic biomass to actually swell, because when the pressure is released, the biomass swells. The lignin distribution of biomass remains almost the same, but the bonds are weakened, and thus it can go for further enzymatic hydrolysis. There is a supercritical fluid pretreatment. So supercritical fluid is neither liquid nor gas. So it has the properties like densities like gas, and the like densities like liquid, and there is like gas like transport properties of diffusibility and viscosity. So it is being able to penetrate the crystalline structure of lignocellulosic biomass in ways that other pretreatment strategies have not come close. But what is the backdrop of this process? The backdrop of this process is it is very expensive process, because the whole equipment, whole pressure generation, and like the small changes in temperature, pressure, that the critical point or TC can make the process easier. But for that to achieve, we require precision based equipments and also very skilled workers to develop the process. Now it comes to alkaline pretreatment. It's a broad area of pretreatment used for generations like sodium hydroxide or potassium hydroxide. the use of alkali causes the degradation of esters and glycosidic side chains, resulting in structural alterations, lignin, cellulose swellings, and also the partial solvation of hemicellulose. And it has been studied for many years for its ability to make the substrate more accessible to enzymes. And also there is lime pretreatment, which is another type of alkali based pretreatment. So what happens in alkali based pretreatment is found out there is extensive delignification which is sufficient for further saccharification. Like acid pretreatment is the most used acid pretreatment. Acid pretreatment is mostly used using dilute sulfuric acid. It breaks almost all the bonds in the biomass, makes it more accessible. Also, it also performs a portion of hydrolysis of the sugars, but it is very also it kind of inexpensive, but it uses acids which is not a good or nature loving substance. And also in acid pretreatment there is the generation of furfural 5 hydroxymethyl furfural, which is one of the major uh, inhibitors for the fermentation process later on. So there are also weight oxidation and ozonolysis where ozone is used. This has almost no side effects, if you can say, but again, this ozonification is a bit pricey. Now we come to the enzymatic and microbial pretreatment. So lignin is primarily broken down via the action of peroxidases and lacases and additional oxidative enzymes like manganese peroxidase or lignin peroxidase. So the enzyme generate the aromatic radicals that cleave the linkages in the lignin molecules. And we also find that some natural and genetically modified bacteria have the ways to utilize the simple aromatic compounds to create products that can be hydrolyzed, like what in the previous session it was discussed how Pseudomonas putida was able to utilize those aromatic products like coumarins and etc. to produce polyhydroxyalkanoids. We have already discussed that. And so one of the major impact is what are the challenges in lignin hydrolyzation. So lignin has a very different bond cleavage structure, like the aryl C bonds, like the CO ether bonds or CC bonds, are almost chemically inert and does not respond to usually hydrolytic enzymes. So the requirement of pretreatment is required. Also, the native lignins are not like the after the alkali pretreated lignins, like the Kraft lignin or lignosulfonate. The native lignin is not soluble in water. So all the process except ionic liquids are using water as the pretreatment medium to reach the substrate and make it more hydrolyzable. So that increases the cost. So lignin is like highly heterogeneous and each molecule differs from the other. So enzyme being site specific, it faces some problems in some degrading some lignin molecules. That has to be studied. Recalcitrance of lignin is a big issue while dealing with delignification. The lignin depolymerization enzyme as also catalyzes the repolymerization of those enzymes where like the time is not optimized and produces high molecular weights. And also sometimes during the pre-treatment procedures, it from oligomeric fragments and other low molecular undesired components that can hamper fermentation process or other lignin derived process. So the scope lies in lignin valorization and for hydrodeoxygenation to obtain smaller number of deoxygenated alkanes. There are also certain steps which are recently being developed to convert those lignin components into high octane alkanes for use as biofuels. So some different enzymes is given here, like lacase from streptomyces. These are all copper containing enzymes which are very effective in dealing with degradation of lignin compounds. So I'll now come to the production of lacase production. So lacquer production was found out. So 32 degrees centigrade, the lacquer was optimally produced at the ambient activity and lacquer level activity. So we found it is a mesophilic fungus, and this lacquer fungus is homegrown. We isolated it in the lab. Also, the pH was found to be 7. The incubation time of 8 to 12 days is found out during optimization procedure, and the solid to liquid ratio is 1 is to 2 or 1 is to 3 best. 1 is to 2 is 1 is to 3 is like best. For that we found out. Now we chose sugarcane crop because it is a C3 crop. It is high efficiency in converting solar energy to bioenergy. Also, it is a sugar containing crop. Even the waste products contains a lot amount of pea sugar and other cellulosic components which can be used to convert into 2G bioethanol. Like in a 1 hectare land, about 70 ton is 17 ton of bagasse is found. So enough bagasse to be used for biofuel generation. Like sugarcane bagasse is there, like almost similar to wheat straw and rice straw in India. So when we studied the effect of solid loading on delignification, we found that 20% solid loading was most effective, maximize delignification in the process. No increase is necessary or decrease is necessary. The time we found out like 6 hours for significant increase in delignification observed. In case of temperature, it was 40 degrees centigrade. In case of pH, it was 7 pH, and for that reason, we were lucky that we could do it at neutral pH and no other change in pH was required. Like GC chromatogram for degradation of products, like in 1 hour and 8 hours of treatment with lacquer, is found that these products are found with some products like there are many products like chromome, like methanol. These are all useful products in the perfume industry. You can see that salbutamol is there. Uh, Salbutamol is there. This salbutamol is a very important product nowadays for making inhaler and something, and all other products can be converted for further studies so that the ligneous component can be valorized. Like this is the HPLC chromatogram of lignin regulatory products over time. You can see that from 1 hour to 8 hours, the peak size increases. So we found out that lignin degradation products also increases over time, and that's why you can assess that the true delignification was from. This is the final and ultimate biochemical and ultimate analysis of raw bagasse, and after pre-treated bagasse, we use the cellulose percentage increases, and also the carbonaceous compound also increases. This is the same analysis of sugarcane bagasse and sugarcane. This is a physical formation of, you can see that there is a cracks and more accessible after pre-treatment the sugarcane bagasse becomes. So conclusion, lignolytic enzymes were able to efficiently degrade lignin in sugarcane bagasse with maximum delignification, and composition analysis and GCMS analysis showed that there was less amount of toxic inhibitors like ferbural and hydroxyferbural for further fermentation procedure. Thank you.
Thank you very much, Mr. Banerjee. We are open to um, questions. Okay, thank you. Then we'll move on to the next speaker. Our second speaker is Mr. Devajyoti Kundu, PhD scholar from Agriculture and Food Engineering Department. He will talk on a sustainable biorefinery approach for conversion of Assam lemon waste into bioethanol and biomethane. Mr. Kundu, please.
Yes. Hello.
Hello.
Can everyone hear the slides? Hello. Can you please?
The slides are not visible yet.
Now? Is it okay?
Yes, they're visible.
Okay. I'm Debojyoti Kondo, a PhD scholar of Agriculture and Food Engineering Department. I am working under the supervision of the Professor Aindrila and the Professor Sandeepan Karmakar. My presentation topic is a sustainable biorefinery approach on the conservation of Assam lemon waste, bioconversion of Assam lemon waste into bioethanol and biomethane. First, I would like to talk about the fuel. Fuel, it's an inevitable source of the energy required in transport and other industrial sectors. It is a driving force to drag all the sectors like transport, industry, domestic, and agriculture. Without the fuel, it cannot be go smoothly to run all these sectors. Then, if you see the contribution of the fuel in different sectors like transportation, industry, commercial, residential. Industry hold a special area followed by transportation, residential and commercial. Thus, we cannot think our life, day-to-day life and societal activities without any oil. Different types of industrial activities, industrial products are solely dependent on the fuel, get fossil-based fuel like medicine, cosmetics, plastics, synthetic rubber, cleaning products, even the production of the road, asphalt, which is made from the fuel-grade product. But there are different negative impact of fossil fuels on the environment. Like fossil fuels are non-renewable in nature. During the production, they are very dangerous. Exploding refineries and oil rigs also. Sometimes the spill of the oil tanks contributing the water pollution. Sometimes fracking to extract the fossil fuels, water table are getting contaminated. Different types of aquifer are getting contaminated. And from the emission, air pollution are occurred and smog are formed, acid rain, mercury emission, global warming and land use pattern, and there is an adverse effect on the biodiversity, flora and fauna. Thus, despite of all this negative impact, till now fossil fuel have hold a very special niche in our society. If you see the greenhouse gas emission contribution from the fossil fuels, we can see the transportation fuel contributes 14% greenhouse gas emission, where carbon dioxide only contributes in 19.2 percentage. Then come to the primary energy demand by different sectors. There is a hike of the demand in the different sector like transport, industry and the building sectors, different sectors. There is a hike of the requirement of the primary energy demand. If you can see that from 2020 to 2030 and 2040, in transport sector the energy demand will be 1.09 fold and 1.19 fold in more demand from the present scenario. Similarly, in the industry sector, there will also be hike in 1.1 fold, 11 fold, and 1.20 fold in 2030 and 2040, respectively. If we categorized the demand of fuel by different types of fuel, we can see there is a hike in the renewable energy in 2040. From now, there will be a increasing demand of renewable energy, when there will be decrease in the fossil fuels, like you can see that the decrease in the coal demand and the oil demand will also decrease. Renewable energy demand will be increased gradually. Fossil fuels, but the limit, there is a source of limit, because the fossil fuel is not a unlimited source. We cannot get for prolonged time. This gap represent two types of reservoir of the fossil fuel. One is proven and another is ultimate recoverable reservoir, when we considered 1.5 and 3% economic growth. Okay, then if ultimate recoverable reserve will be diminished by 2110 and 2090, when 1.5% and 3% growth has been considered, and the proven reservoir will be diminished by 2090 and 2070, when 1.5 and 3% growth has been considered. This is the, in a nutshell, how many years we will be enjoying our different types of fossil fuel like coal, gas, oil. It is predicted that 132 years coal reservoir will be available, what is proven reservoir, and the gas reservoir will be available by 51 years, and the oil reservoir will be available by 50 years. Though fossil fuel is the largest source of the global energy, depleting resource make it unstable and limit in its use. Thus, there is alarming concern. The scarcity of liquid fuel also make lead to international conflict. Considering these different types of problem, new policies have been made formulated to encourage the expansion of the renewable energy source with the special emphasis on biofuel. And the other, hence, in these circumstances, biofuel can be a viable answer to world surging energy needs and can also act as a promising carbon neutral fuel resource. If we categorize different types of fuel, the fuels are categorized from the biomass through different process. Different types of biofuel can be produced, which are gaseous, maybe gaseous, liquid, and solid. In this presentation, I will be mainly talking on the gaseous fuel such as methane and liquid fuel ethanol. If you see the history of the bioethanol production, we can see that the bioethanol production was first found in 9,000 years ago in China. Sugarcane is the oldest feedstock, considered as the oldest feedstock for the bioethanol production, which has been used for the bioethanol production since 6,000 before Common Era. If you see the chronological of the bioethanol production, in the 12th century, ethanol was first produced in the Ireland from the starch-based material. Then in 80s, corn-based alcohol, which was produced from the corn, was used to lighting the lamp. Then in 1826, grain-based ethanol was first used in ICE engine. Then in 1880s, grain ethanol was first used in the automobile. This automobile was also presented in an alcohol fuel examination in Paris. Then in the early 90s, bioethanol use of the bioethanol was increased in the Europe and America. In the 1980s, the Ford Model T car was manufactured, and it was able to use ethanol or any mixture of ethanol and gasoline as a fuel. Then in 1975, in Brazil, they are very much producer of the ethanol from the sugarcane. They started to develop different types of quality for the production or use of the ethanol from the sugarcane. Then in 1984, blended ethanol was used in the car, mixed with petrol, gasoline, etc. At present, the scenario, we all know the world is driving or running towards the production of the ethanol from the defined source, not only from the crop-based product. There are depending on the different types of source, the ethanol production also categorized from first generation to third generation and fourth generation biofuel. This is the picture given. Ford Model A car in 1896, which was used purely ethanol based, and the latter in Rudolf Diesel, a German engineer, also filed a patent on the compression ignition engine in the year of 1894, and after that in 1897 he was successfully operated a prototype engine from the fuel. If you see the demerits of the use of the gas, different types of fossil based fuel. Fossil-based fuel, we can see that rather than the traditional gasoline, starch-based biofuel, use of the starch-based biofuel decreased the 43% carbon dioxide emission, while cellulosic biofuel will be considered for the reduction in the 85 to 95% cellulosic carbon dioxide emission. Then to address different types of environmental issues such as depletion of the coal reservoir, depletion of the oil supply, depletion of the oil reservoir, sea level rise and gas reservoir, extreme weather condition and global warming condition, Indian government launched ethanol blending program, that is means EBP program in the 2003 for undertaking blending on ethanol program. There is a huge benefits for the use of the biofuel than fossil fuels, because it emits less greenhouse gas emission, less pollution than the other conventional fossil fuel. Then ethanol fuel mixes world scenario, different types of country like Western Europe, USA, Brazil are using different blending ratio, like 5% ethanol with 95% gasoline, what is considered as E5 to E10, E15, and E25. That is mixing of the 10% ethanol, 15% blending is considered for the USA EPA approved cars, and 25% blending is considered as Brazil for the regular vehicles. And on the other hand, USA and Brazil is using 85% blending and 100% blending respectively for the flexible fuel vehicles. Ethanol blending program Indian study, if you see that the blending proportion is considerably is increasing day by day. If we see that 2010 it was the percentage of the blending was 0.3%, now it is 5.8% in 2019. Gradually it may be increased. And presently EBP is being done in 21 states and 4 union territories of the country. In India, ethanol is a primary manufactured by the fermentation of molasses and byproducts of the sugarcane crushing process, and nowadays the different types of lignocellulosic materials, different algal biomass is using for the production of the ethanol. Then it's the overview of the ethanol in India. If you see there's a graph, we can see that the consumption is greater than the production. Then there is a requirement in the ethanol import in our country. Thus there is an imbalance between the supply and demand. To minimize this imbalance, we need more focus for the production of the ethanol from different source, reliable source, which can be round the year available for different types of agriculture waste. We can be convert from the bioethanol production. These are the some source from which bioethanol can be produced, like waste, oil, fats, and algae, municipal solid waste, and cellulosic biomass. These are the some strategies for the bioethanol production, like separate hydrolysis fermentation, separate hydrolysis and co-fermentation, simultaneous saccharification fermentation, simultaneous saccharification co-fermentation, pre-saccharification followed by simultaneous saccharification fermentation, partial enzymatic saccharification, co-fermentation, and concentrated bioprocessing. Different types of process has been adopted to evaluate the ethanol production process and to improve the ethanol yield inconsequently. Along with the bioethanol production, another gaseous biofuel is the biogas, which is also renewable in nature. Different types of biomass like energy crops, manure, industrial waste, municipal solid waste, restaurant waste, and wastewater sludge can be used for the biogas production, which ultimately which can use for the cooking, electricity production, renewable product, and the residues after biogas production can be used as a biofertilizer and biomanure also. If you see the biogas market, we can see that the North America market will witness of the rapid growth by 2050. Had Asia specific country industry a compound annual growth rate of 2019-25, it will be increased by 10%, and for the European market it will be increased by 7% by 2050. Biogas market size was valued over 70 USD billion in 2018 and is anticipated to witness growth of 7% by 2025. If you see the state-wise installed bio-CNG capacity, the Maharashtra is the leading state, where total 5 number of plants has been established with the capacity of 16 kg per day, following the Gujarat, Uttarakhand, Rajasthan, Haryana, Uttar Pradesh, Punjab, Madhya Pradesh, and Tamil Nadu. These the biogas have a potentiality to replace the fuel wood, because basically biogas is used for the cooking purpose, and the fuel wood is the major contributor in this to for the cooking purpose. We can replace the biofuel fuel wood to the biogas. You can see the different states like Chhattisgarh is in the highest sensitivity zone in terms of biogas replacement potential. The states of Kerala, Goa, Tripura, Mizoram shows a low potential zone, and in the high potential for harnessing of the potential of biogas is anticipated by Andhra Pradesh, Madhya Pradesh, Haryana, western part of Uttar Pradesh, Rajasthan, and Bihar. Then if you see the history of the biogas, John Baptista van Helmont determined in 1963 that flammable gas could evolve from the decaying of organic matter. After that, in 1776, Count Alessandro Volta found a correlation between the amount of decaying organic matter and the amount of flammable gas produced. In 1764, anaerobic digestion was first discovered by Benjamin Franklin. Later, in Sir Humphrey Davy determined that methane was present in the decay process in 1888. This is the process by which the anaerobic digestion was carried out and biogas biomethane has been produced. There are basically three steps. Another is and one is hydrolysis, and this acidogenesis and methanogenesis. Firstly, carbohydrate, proteins, and lipid are hydrolyzed in different types of sugar, amino acids, long chain fatty acids, and alcohols. And after that, in methanolic states, after that acidogenesis state, volatile sugar, amino acid, long chain fatty acid, alcohol are converted into volatile fatty acids and hydrogen and carbon dioxide, and later in this volatile fatty acid and hydrogen is converted into methane. Carbon dioxide is as a major part and little amount of H2O and hydrogen sulfide. Basically, in anaerobic digestion process, three groups of microorganisms are involved: group 1 and group 2 and group 3 considered. Group 1 microorganisms are like Actinomyces, Aridobacter, Clostridium, Pseudomonas, and Ruminococcus are used for the hydrolysis process. And in the group 2 microorganism, different types of Clostridium species has been involved in the acidogenesis process, and different types of Methanobacterium are involved in the methanogenesis process for the production of the methane. If you see the heating value of biogas, we can see the 1 cubic meter of biogas is equivalent to, can replace 1.5 kg of firewood, 1.2 kilowatt hour of electricity, 0.55 liter of fuel oil, 0.6 liter of diesel oil, and 0.46 kg of LPG. But what can we do with this 1 cubic meter of biogas? We can light up 60 to 100 watt lamp for 6 hours. A family can cook 3 meals using this 1 cubic meter of biogas, and 1 horsepower motor can be worked for 2 hours. Then it is the overall scenario from different types of manure, cow dung, different types of dung, how much amount of biogas can be produced. From here we can see the poultry manures has the highest potentiality to produce the biomanure comparing the other sources. Basically, biogas is primarily content of the methane and carbon dioxide, and have some amount of hydrogen sulfide. Methane content concentration is varied from 50 to 75%. Carbon dioxide varies from 25 to 50%. Nitrogen is 0 to 10%. Hydrogen is 0 to 1%, and hydrogen sulfide 0 to 30%. And in India, there are 3 types of biogas plant depending on the community based and area size. There are 3 types of biogas, like 1 to 25 cubic meter per day, which is has been used for household purpose like fixed dome and floating dome. Community based biogas 22,000 cubic meter per day, which is which mainly used for KVIC, Nisarguna, decentralized containerized solution. And a large scale biogas plant, like which is capacity is greater than 2,500 cubic meter per day. It is basically flow anaerobic surge bed reactor, CSTR, plug flow type reactor, and regul type reactor. This is the scenario in India, which is how the grid connection from the biogas plant till 2017 from the 152 biogas plant, 223 megawatt capacity, electric capacity has been installed, and where off-grid biogas plant contribute in the 260 number of plants, and 5.5 megawatt electric capacity has been installed. Then now biogas application for the transport fuel has been implemented in the biogas bus in Sweden, the biogas train Amanda in Sweden. And there is huge opportunity for the increment of the methane concentration, yield of the biogas from the defined substrate for the biogas plant, energy consumption and nutrient recycling in the biogas system, high value product and derivation from this from the anaerobic digestion process, etc. Thus, come to the different types of substrate which can be used for the biofuel. Then solid food waste has a high cellulosic content, represent as a potential candidate for the bioethanol production. Citrus fruit has immense potentiality for the biogas production because it has a high richness of the fermentable sugar. Thus, utilization of the citrus waste, processing waste, which in the citrus processing waste, like industry which are making juice, can be a industrial symbiosis process by another industry which are using the waste for different valorization product. Another thing is the regulation concern organic waste and demand of renewable biochemicals and fuels driving us to make a virtue out of necessity towards sustainability, cost effectiveness, and to meet our consumer demands. We cannot throw the waste according to the solid waste and management handling rules 2020. We cannot we cannot dump the solid waste simply without valorization the waste. If you see the citrus production, we can see that the India holds the third rank production in citrus production after China and Brazil. In different processing step, a huge amount of waste can be generated from the citrus processing waste, which can be further valorized. The about 50% of the whole fruit waste are generated from the waste. This is the integrated biorefinery approach for complete validation in a closed loop process. We can see that from the starting from the sited cultivation and after the biogas production, different types of energy production, the residue can be used as a biofertilizer, which can be come back in the citrus cultivation, and in the every step, and we can generate some revenue generation in a bioeconomic circular bioeconomic process. This is a strategic strategy for the bioethanol production from the Assam lemon waste. Assam lemon waste, basically Assam lemon waste is plenty available in the northeast part of the India, which is the reservoir of the citrus species. A partial simultaneous saccharification and co-fermentation was implemented to overcome the mismatch of the temperature in the fermentation process. Initially, prior to the ethanol production, pectin was isolated from the pill, where 12.657% pectin was derived, and from the Assam lemon pill, 4.19% ethanol essential oil was extracted from the pill, in which limonene 94.47% ethanol was limonene was the component. And this is the composition analysis of the waste. For the partial sacrifice, two types of NGM dose and time was considered. And for the ethanol production process, different types of process, solid loading, incubation time, temperature, and hentose to hexose fermenting strain ratio was considered. After that, analysis of variance was carried out, and a response surface methodology based optimization was done to optimize the process, and the process was highly significant at 99% confidence level. The optimization plot depicts that the present study exhibit 12.04% ethanol concentration. This is the material flow study for the whole process. After that, we can the surface area has been increased. Ultimate analysis value of the ultimate analysis was decreased, and the cross calorific value of the substrate after fermentation was decreased. Cellulose crystallinity was decreased by 19.4%. Different types of peak area in the FTR analysis was decreased after the fermentation process. There is a clear view of the distortion of the structural changes in the same analysis before fermentation and after fermentation. After bioethanol production, the fermented residues were used for the biogas production. Where biogas production, the composition analysis as depicted in this slide. And prior to the biogas production, different types of process like volatile fatty acid composition and pH was evaluated in the presence of the graphene oxide and the absence of the graphene oxide. Graphene oxide used for the present study to accelerate the direct electron transport amongst the microorganism. Different single variables approach of biomethane production like cumulative methane days, solid loading, inoculum volume, and graphene oxide concentration was evaluated. From the optimization study, RSM based optimization study was considered, from where we can see the model in its linear squared and injection was significant. And from the interaction plot optimization, it was exhibit that the 243.23 ml per gram methane was produced per gram of volatile solid feed. Kinetic analysis also carried out, from where we can see that the modified Gompertz model was best fitted model for the current study. A material flow analysis was carried out for the biogas production from the fermented Assam lemon waste, which is depicted in this slide. And after that, the characterization of the different types of characterization of the substrate and digestion substrate before and fermented and digested was evaluated, from where we can see that digested biomass, surface area, pore volume, and the pore radius has been increased, where the different types of elemental composition like carbon, hydrogen, nitrogen, sulfur all decreased decreased considerably. Gross calorific value of the digested and fermented biomass, also where the fermented biomass gas calorific value was 12.72 megajoule per kg and the digested biomass was 8.62 megajoule per kg. In the XRT analysis, there was a decrease in the reduction in the crispinity index in the digested biomass comparing to the fermented Assam lemon waste. A decrease of 18.4% in cellulose crispinity has been found. In FTR peak, also in the region of the 890 to 1200 centimeters, implied the abundance of the carbohydrate molecules. Peak in the 1018, 1053, and 1100 and 1153 centimeter inverts are linked with the carbon oxygen carbon hydrogen stretching in the sugar and the COC stretching of the beta 1,4 glycosidic bond between the sugar moieties. All the peak intensity had been decreased in the digested Assam lemon waste. In a nutshell, we can see that at 30% solid loading, 24-hour incubation time and 35% centigrade temperature and 0.5 pentos to hexose utilizing strain ratio, maximum ethanol production, that is the more than 12% ethanol has been was achieved at 25% gram per total solid loading per total solid per liter of solid loading and 30 days incubation time and 1% uniform volume and 0.06% graphene concentration exhibit the maximum methane concentration, that is 243 ml per gram of volatile solids feeds. And different types of characterization study like XRD, SAME, and FTR study exhibit the complete biotransformation of the cellulosic materials, and SAME analysis establish the deconstruction of the biomass structure due to the enzymatic action. The waste generated after biomethane production can also be used for the biomanure production that will make the process economically viable and which will be make the process as a closed loop for circular bioeconomic approach. Thank you.
Thank you, Mr. Kundu, for the nice talk. We are open to questions. So now we shall proceed to the lecture sessions. The first lecture will be given by Professor Makarand M. Gangrekar. He is a professor in the Department of Civil Engineering, IIT Kharagpur, and the heads of P.K. Sinha Center for Bioenergy and Renewables, as well as School of Environmental Science and Engineering at IIT Kharagpur. He earned his Masters of Technology degree in Environmental Engineering from VNIT Nagpur in 1991 and his PhD degree on Environmental Science and Engineering from IIT Bombay in 1998. He has been associated with IIT Kharagpur for the last 16 years and works predominantly on microbial fuel cells, UASB reactor for anaerobic wastewater treatment, water and wastewater treatment, bioenergy recovery from during waste management, and wastewater reuse. He has received the Alexander von Humboldt Fellowship in 2013 and is the two-time recipient of Gandhian Young Technology Innovation Awards for the years 2015 and 2016. I request Professor Gangrekar to kindly deliver his talk. Sir, please.
Thank you, Manali Das, for nice piece of introduction. And I'm very happy to start in time. So let me share the screen first. Just confirm, am I audible as well as the presentation is visible?
Yes, sir. Everything is fine, sir.
Okay, fine. So I presume that my voice is also reachable to all of you. And once again, welcome you to this interdisciplinary workshop on recent developments in bioenergy research. I hope in the morning session, the participants must have been benefited and got exposed to newer technology. Here, I am going to present the work that we do majorly at IIT Kharagpur on bioelectrochemical systems with a little bit background of what really bioelectrochemical systems mean. So, okay. So this will be the contents of my presentation, typically touching upon the background, bioelectrochemical processes in general, microbial fuel cells in particular, different components involved in these BA systems, the challenges ahead of the BA systems, and what efforts we have taken at IIT Kharagpur to scale up this MFC and other bioelectrochemical based systems to develop the concept, what we call it as a bioelectric toilet. So you are all aware, being in this field, doing research in this field, how challenging is the curbing water pollution problem. The presently used technology demands higher amount of energy for treatment of this wastewater. And the scenario, particularly in Indian context, is not that good. Only about 30% of the wastewater generated in this country is being treated properly before it is discharged into the water body. And since 80s, people have been working on development of anaerobic processes, where I started my early career on designing of the USB reactor for sewage treatment. However, sewage and industrial wastewater treatment. However, over the period of time, it is realized that for a small scale USB reactor, if you generate a methane, economically it is not viable to convert it into electricity. Unless you are consuming on site, it is fine. But if electricity is the final goal, that is not feasible for 1 MLD or less capacity sewage treatment plant. And generally, the methane generated from such anaerobic reactors or USB reactors is flared on site, and then we are losing the opportunity to be capturing the methane as an energy source. So then we started thinking, and since 2004, we are undertaking research at IIT Kharagpur on development of bioelectrochemical processes. That is a broader umbrella under which different configurations of the BS comes in. The microbial fuel cell is the most popularly researched configuration under BS. So what it is, the microbial fuel cell consists of two chambers, anodic chamber and cathodic chamber. As shown in the animation, the respective electrodes are housed in this chamber. On anode, electrogenic bacteria typically are targeted to get cultured. So these bacteria will utilize the organic matter, that is the wastewater that we would like to treat, that will be admitted, that is working as a fuel in this anodic chamber. So this organic matter will work as a substrate for these electrogens, and it will get converted into protons and electrons. These electrons will pass through the external circuit towards cathode. Protons will be allowed to pass through the proton exchange membrane, which separates the anodic and cathodic chamber. And on cathode, in the cathodic chamber, typically aeration is being carried out to supply oxygen. And on cathode, this oxygen, dissolved oxygen, electrons, and these protons are combined together to form H2. So in this way, the electron flow is initiated, and this way the current electricity will be generated in the circuit, and we can use that electricity for powering certain on-site devices. So this is the basic concept of microbial fuels. The advantages that BS offers, they are sustainable green energy source. So the fuel that we are using is the organic matter that is recently fixed carbon from the atmosphere that we are using. So it is a carbon neutral energy source. To generate electricity from various type of organic waste, almost all range of wastewater have been tried by scientists so far for effective treatment in the microbial fuel cell. It converts chemical energy stored in the organic matter directly in a one step, single step into electricity. Suppose if you want to go by anaerobic pathway, generating methane. So at every stage, we have energy loss, because typically the IC engines that we are popularly using, they give not more than 35% conversion efficiency. So huge loss of energy can occur. So here in this case, so being a one-step process, we can expect much more energy gain. High energy conversion efficiency thus can be obtained, operated efficiently at ambient as well as low temperature. So we don't need higher temperature as required in some of the other fuel cells. It can be operated at ambient temperature range. Sludge production is at par with the anaerobic process, so very less sludge is produced as compared to the counter aerobic processes. Do not require any off-gas treatment as required. Biogas reforming is required if you want to utilize methane generated from the anaerobic reactor. Whereas here in this case, this is not necessary, because off-gas is only CO2. No energy required for aeration, provided the cathode is passively aerated. So as shown here, This is what we call it as aqueous cathode arrangement. We can make the cathode electrode assembly in such a way that cathode is placed along with this PEM, and directly oxygen from the air can be breathed. That we call it as a air cathode microbial fuel cell configuration, which will not need any aeration, and even the minor aeration cost also can be eliminated for operation of microbial fuel cell. The energy recovery in the BS could be either bioelectricity, or if we configure BS, even more pure methane as well as hydrogen can also be recovered in the cathodic chamber of BS, or it can be exploited for various other resources recovery such as metals, nitrogen, potassium, phosphorus can be recovered, or even high value chemicals can also be synthesis using different configuration of BS. Though the initial research was exciting, however, there are bottlenecks and challenges ahead for practical application of the system. The major challenge is regeneration of power output from the system as compared to the chemical fuel cell. We are using bacteria as a catalyst, so the rate is limited with the bacterial rate of metabolism, and we have to live with that. Then there are intrinsic losses that are unavoidable. Activation loss, any reaction to take forward, there will be some loss. Concentration loss that will occur because of the diffusion limitation that will occur near the electrode surface. And when any charge is flowing, the ohmic loss is bound to occur in the system. So all these three put together, it will decide the internal loss of the losses in the system, and will decide the resistance of the system. And to harvest more electricity from the system, we need to target that the internal resistance should be kept as low as possible. Scaling up of the system is another challenge, like the earlier speaker talked about, Mr. Kundu. The anaerobic reactor could be a single large reactor of 300, 500 meter cube capacity. Whereas in bioelectrochemical system, each reactor need to be as small as possible, because our substrate should move as close to the electrode as possible. If I make a very large reactor of 500 meter cube, most of my substrate, that is wastewater, will flow away from the electrode, and substrate conversion will not occur. That is one of the limitation, chemical engineering limitation. And the other limitation is the electricity that generated by the bacteria. Say, for example, if we are degrading acetate in the anodic side, the voltage generation is minus 300 millivolt. And if we are using oxygen as a terminal electron acceptor, 805 plus 805 millivolt is the oxygen reduction potential that will be generated on cathode. So put together, the theoretical voltage that will be generated by each cell will be only 1.1 volt. However, when you take all this into account, practically the voltage generation that is observed in the MFC, each MFC is in the range of 0.5 to 0.7 volt. So 500 to 700 millivolt. So if I make single 100 meter cube larger reactor, it will only give me 0.5 volt, and that will be useless electricity to power anything. So I need multiple reactors, either to put in parallel to integrate current, or some of the reactors should be put in series to integrate voltage, so that usable electricity can be produced. So that limits the scaling up of the system. Expensive electrode assembly, the material that we are using, the metal catalyst that we are using, they are costly, and that increases the capital cost of this device. Then there are operational issues like pH imbalance, current fluctuation, high internal resistance which will come up over the period of time. So that need to be overcome to make it practicable, and high maintenance cost expected, because the membrane that we are using, the proton exchange membrane for separating anodic and cathodic chamber, that is extremely costly. I will come to that. Whereas it has several applications in the life sciences, such as it could be exploited for wastewater treatment, it could be used itself as a BOD sensors, and commercially these products are available now. It could be used for removal of hydrocarbons from sediments. So any polluted sediment, you can place the anode in the anoxic zone, and cathode could be placed in the aerated zone on the top. And thus, setting up this electrical connection, we can in situ remediate the polluted water body or the sediments. Power generated from the sediment can be used for powering remote sensors, and this is in practice applied in the Europe to power the environmental sensors by exploring the organic matter settle on the sea floor. So this way, sediment MFC has been explored for powering remote environmental sensors and monitoring system. The BS has a potential to provide long-term, stable, and low power for biomedical devices implanted into human bodies. So that way, also the enzymatic fuel cell, if we make it, they can be exploited. The mediated MFCs can be exploited for rapid detection of bacterial food contamination. It could also be used for degradation of the sludge, like anaerobic digester. We can use it as a bioelectrochemical digester. So this digester, our experience, instead of 25 to 30 days required typically for conventional digester, we can digest this sludge within 7 to 8 days, and that too requiring much more electricity directly for on-site application. So that way also it could be explored. Simultaneously, secondary treatment, that is organic matter removal, as well as tertiary treatment such as disinfection and even the desalination of the wastewater is also possible while configuring the system properly. Synthesis of organic compounds using CO2 as a source. So carbon sequestration is also feasible by properly configuring the BES. So this way it has several applications as shown in the photographs. The same thing has been shown here in these photographs. The components involved in the BES, they are anodes. So that is the basic anode electrode. Typically, the material properties required here are the material should not get weathered by itself. It should be biocompatible to allow the growth of bacteria. It should have high conductivity, so less internal resistance. So these are the property expected, and hence the conductive metal like copper, nickel cannot be used because the leaching of those metals will be toxic to the bacteria. So typically, carbon-based materials are very popularly used, but platinum black, stainless steels are also being used to be anode material in the BS. Cathode, again, the properties expected are cathode could be operated as a biotic or abiotic cathode. So if we are not going for biotic cathode, so in case of abiotic cathode, biocompatibility is not a requirement. However, the major requirement for the cathode material is the oxygen reduction reaction. Typically, the carbon-based electrodes which are used have sluggish oxygen reduction reaction, and hence carbon-based material with catalyst traditionally used platinum or any variety or different composition of the mixed metal are being used to enhance this ORR, oxygen reduction reaction on cathode, so that the higher cathodic potential can be obtained. Stainless steel is also being used as a cathode material. The proton exchange membrane that is being used is the one of the costliest atom for fabrication, and Nafion is the popularly used proton exchange membrane manufactured by DuPont, USA, and that cost around 1,500 US dollar per meter square of the piece of the membrane. So that makes the preposition extremely costly. So fabrication of MFC will get it will become expensive because of the use of Nafion. Ultrex is the alternate membrane costing around 800 to 900 euro per meter square. However, still it is still making it too costly. Other alternatives like salt bridge or porcelain septum, though they are cheaper, but they will increase the internal resistance of the system to such an extent that the electricity harvesting capability will get compromised by using such separator. Cathode catalyst I already touched upon. The catholite, the oxygen available in air is cheap, but we have to spend the cost for aeration, little energy we have to spend. But that is what traditionally or popularly being explored as a terminal electron acceptor in the cathodic chamber. Whereas to enhance power, we can even use ferricyanide, means chemical catholite like permagnets can also be explored. But then periodically we need replacement of those chemical catholite, and that may not make the process sustainable. The separator influences the performance of BS considerably, and that cost around 40 to 50% of the capital investment is addressed to this separator, and hence this is a major bottleneck that hinder the scalability of this BS or microbial fuel cell in particular. The ideal separator should not allow oxygen from cathodic chamber to diffuse to the anodic chamber, otherwise there will be direct substrate loss because of the aerobic oxidation. It should also not allow the anodic substrate to diffuse towards cathode. Otherwise, it's a physical substrate loss, and hence will lessen the electricity production. And it should allow protons only to pass through from anodic chamber to the cathodic chamber. So these are the properties expected from ideal separator. The internal resistance decreases considerably when we are using wider area of the proton exchange membrane, but because Nephron being costly, scientists have been trying with only small piece of membrane to separate, and that increases the overall internal resistance of the system. The factors that affect the BS performance, they are inoculum type and concentration, what the bacteria that we are looking at, as shown by earlier presenter. Here, the presence of methanogens is an enemy for me, because these methanogens will consume the substrate, and this substrate will not be available for electrogens, and in this way the electricity generated in the microbial fail cell will get reduced because of the utilization of substrate by the methanogens. So what I need a culture which is enriched in the electrogens. So the commonly available inoculum is the anaerobic sludge that we have been traditionally using, with some pre-treatment to suppress the activity of methanogens. But over the period of time, again methanogens will take up, because of the similar conditions which are favorable for their growth and sustenance. So there is always a competition that will be faced by methanogens to the electrogens. The geometrical design, as I said, the major challenge is to design a system in such a way that wastewater is forced to flow close to the electrode. The electrode materials and catalyst we just talked about, and then the operating parameter as pertaining to any other technology, treatment technology. These parameters such as pH, operating temperature, organic loading rates, and also here in this case, additional parameter, the internal resistance, will also affect the performance of the BES. In the umbrella of BES, the variant majorly researched, they are MFC, microbial fail cell, MAC, microbial electrolysis cell, MDC, microbial desalination cell, MES, microbial electrosynthesis cell, and then the other variants such as sediment microbial fail cell, which are in the working principle similar to MFC, or microbial carbon capture cell. This is again a modification of microbial fail cell. This will give you the importance of this topic and the attention the scientists have shown till last year 2019. This is the statistics. So you can see the different variant of MFC, MES, MTC, MCC that are constructed wetland MFC. So out of these, MFC is the by and large the largest investigated device, and this is the latest update till last month. Number of publication that we are having this month, the publication number has crossed even 1100 now. So every day almost 3 papers are being getting published to address different aspect of BES. And here where we stand in IIT Kharagpur, personally our lab research group stands among top 3 researcher in this domain, contributing 132 research article addressing different applications or different material required for the microbial fail cell. And as an institute, we stand in the rank of 5th all over the world, who are contributing for development of this device. So this different configuration we already touched upon. The MDC is basically the configuration where we configure a system in such a way that apart from the organic matter oxidation, it will also help me in facilitating desalination. MCC is the microbial carbon capture cell, which will work all the requirement of the MFC. In addition to that, it will also try for carbon sequestration and culturing algae in the cathodic chamber, so that the photosynthetic algal will supply oxygen, and that way the active aeration can be avoided and the cost of operation of the MFC can be minimized. The early investigation that we carried out in the lab, actually it worked as a breakthrough, and then people started seeing the pilot scale microbial fail cell, because the proton exchange membrane, the polymer based proton exchange membrane was hindering the scaling up. And now majority of the pilot scale reactor we have, to my knowledge, there are about 8 larger scale pilot scale reactors all over the world, and majority of them are using ceramic membrane separator. We noticed that early days, 2005, 2006, that the natural clay has a cation exchange capability and that could be explored for proton exchange. And with the natural clay, whatever the clayware pots available in India, any size, any shape, so they can exhibit some level of proton transfer number. But as compared to the Nephon, the commercially available polymer membrane, the cation transport and proton transport efficiency of the natural clay is much less. So what we did, we spiked it with the montmorillonite, kaolinite or illite. So these kind of minerals, which are again supposed to be cation exchanger, and then synthesize the membrane. So the M20 membrane, which contains the natural clay available in India, spiked with 20% montmorillonite, that gave us the result comparable to that of Nephon. And using this clayware membrane, initially we characterized this membrane, and you can see the cation transport number of M20, that is 20% montmorillonite containing clayware ceramic membrane. The cation transport number is comparable with that of Nephon, so 0.98, 0.96, so almost similar. And similar other properties we obtained. And using this membrane, the microbial fuel cell could demonstrate about 7.5 watt per meter cube of power generation. The Coulombic efficiency that we obtained utilizing this membrane was 30%. Coulombic efficiency is the measure how much amount of energy that we are able to harvest in terms of electricity to the theoretical energy that is present in the waste water that we are using it as a fuel. So 30% is anyway a good number while using a mixed anaerobic sludge as a inoculum, which has even which is facing competition while facing competition even from the methanogens. And then there are other biolateral chemistry observations. Those who have interest, at the end we might discuss those. So this actually worked as a breakthrough, and there are now pilot plant in apart from IIT Kharagpur, we do have the largest pilot plant at IIT Kharagpur. And apart from ours, there is a pilot plant in UK, then in Ghana, and two other places in African countries, treating actual urine or actual wastewater generated for offering on-site treatment to the wastewater and electricity generation. Then we continued our research, and we observed that the coconut shell, what we are getting, the natural coconut shell itself has a better cation exchange and proton exchange capability. And you can see the difference here. When we compare, we carried out experiment in the MCC configuration here, microbial carbon capture cell. MCCN stands for the MCC using Nephon as a separator, and MCCCS is a is a coconut shell used as a cation exchange membrane separating the anodic and cathodic chamber. So you can see the improvement. The power density in using coconut shell was 3.2 watt per meter cube, whereas for MCC Nephon it was 1.8. But scalability is the issue here, because the coconut shell has a small size. We cannot go for scaling up of this coconut shell. Though we tried with the cement matrix and other thing, but that makes it clumsy. So what we did then in the next effort, we impregnated this activated carbon prepared from coconut shell in the natural clay, and then this composite membrane that we have made. And now see the result, the power density of MCC using this activated carbon from coconut shell with clay was almost double as that of MCC having Nephon. So this is scalable now. We can make it 1 square feet of each tile, and this can be fitted on the scaled up microbial fuel cell. Another challenge that I just touch upon is the competition that is faced by the methanogens. Scientists are using specific chemical inhibitor to inhibit the methanogens in the microbial fuel cell anodic chamber. However, when our primary goal is to treat wastewater, addition of such chemical also would demand the downstream removal of this chemical, and that will add on to the cost of the treatment. So we explored the possibility of Chitosaurus, the marine algae that is available, could be exploited, and hexadecatrionic acid present in this Chitosaurus algae, that itself works as a inhibitor, specific inhibitor to the methanogens. And we tried using sucrose as a carbon substrate with the addition of this marine algae extract. So inhibition of methanogens was successful. We also carried out experiment using this marine algae itself as a substrate, and encouraging result in both cases were obtained. we got Coulombic efficiency here in this case is 47%, which is the highest using mixed culture inoculum in the literature, and using microbial fuel cell of size 2 liter and above. So, so this way the naturally occurring algae or even the other algae also can be spiked into the anodic chamber. Some level of suppression of methanogens they do participate because of the presence of higher chain volatile lipids that it has, and that will help in suppressing the methanogens. Then biofouling control on the cathode is another challenge that is faced by the microbial fuel cell, particularly when we go for air cathode kind of configuration. So these are three air cathode microbial fuel cell configuration. So the first one coated with only carbon, the external surface. This is the cathode. You can see that after 2 months of operation, majorly fungus and then some bacteria growth occurs, and this is SEM micrograph of what the growth has occurred. So because in India the climatic condition here is humid, since we are using ceramic membrane, so it also allows some amount of organic matter to diffuse. So though it has a reasonably low substrate diffusion coefficient, but some level of substrate will anyway get diffused, and because of the availability of nutrients on the surface, so the fungus and then bacteria will start growing. As a result of that, the colony formation here will keep oxygen away from the reactive surface of this cathode, and this will reduce the oxygen reduction reaction, and in process it will reduce the performance of microbial fuel cell. So what we tried with 10% of the carbon powder could be replaced with the silver nanoparticle. So this is the middle one having 10% of silver nanoparticle with much lower loading. The carbon itself is having loading of 1.25 milligram per centimeter square. So 10% of that means 0.125 milligram per centimeter square, and this one has a 20%, so 0.25 milligram per centimeter square. So you can see the change with the 10%. Some patch formation still observed, but in case where we had a 20% silver nanoparticle, almost no biofouling was observed on the cathode surface, and this microbial fuel cell gave us stable performance for more than 3 months of operation without noticing even the minute biofouling on its surface. So these are the clever cylinders coated with the carbon powder with 20% silver nanoparticles in it, and inside the cylinder itself is a anodic chamber of microbial fuel cell, and you can see the electric connections that is coming here in this photograph. These wires are the current collectors. You can clearly see them here where there is a biofouling that has occurred. So this way anode and cathode are connected to make a circuit complete and harvest electricity. So the such metal if we incorporate into the MFC, so apart from the silver using the biocidal property of the silver being used here to control biofouling, the silver also participate in accelerating the ORR, and this way it gave us around 41.5% Coulombic efficiency with 20% nanoparticle. Even with 10% of silver in it, 39% Coulombic efficiency was obtained. So the results are encouraging. As far as the COD removal is concerned, all of them demonstrated better COD removal. However, because of the biofouling, the performance of this MFC control, where there was no silver nanoparticle, you can see considerable drop in performance. For example, the volumetric power density is just less than 2, whereas with 20% silver nanoparticle, nearly 9.5 watt per meter cube of electricity could be harvested from this system. Then we also carried out some experiment on microbial desalination cell. So microbial desalination cell we configure here instead of only 2-chamber system. The chambers could be there could be the middle chamber which works as a desalination chamber. So because of the charge difference between anodic and cathodic chamber, it will force these ions to migrate. So anions will migrate towards anode, cations will migrate towards cathode, and this way the wastewater which is getting treated in the anodic chamber could be admitted to the desalination chamber to facilitate desalination, or separate saline water can also be desalinated. So this way we can get advantage of simultaneous electricity generation as well as facilitating salt removal also from the wastewater. We carried out experiment using synthetic wastewater. We carried out experiment using actual industrial wastewater. This was a research project funded by Tata Steel. Their steel industry effluent wastewater that we tried using 5-chamber microbial desalination cell. Instead of using 3-chamber, we introduced the concentrate chamber in between because the cations migration towards cathode will keep allowed deposition of cations on the cathode, and over the period of time the cathodic oxygen reduction reaction rate will get diminished, will get reduced. So to avoid that, we use a concentrate chamber here, so these cations will get concentrated here, and this way even chemical recovery also is feasible, though we didn't try it, but other scientists have tried upon other chemical recovery or salt recovery even in this concentrate chamber. Similarly, the anions passing to the anode, if higher concentration built up, say for example chloride, then it will adversely affect the bacterial growth rate here. So that also can be trapped in the concentrate chamber, and this is what we tried using the actual industrial wastewater, using pure culture of Pseudomonas, or using mixed culture or combination of mixed and pure culture of Pseudomonas, and reasonably good performance result that we obtained. Particularly, the performance was more encouraging when we used the mixture of both anaerobic sludge as well as pure culture of Pseudomonas 50-50%. That gave us high TDS removal efficiency, high COD removal efficiency, as well as high phenol removal efficiency of more than 90%. Those who are conversant, phenol is not that easily decomposable compound, and using only mixed culture, we got only 58% removal efficiency. So this gives you idea. So, and then the power generation was also possible. And simultaneous desalination, removing 75% of TDS present in the wastewater, actual industrial wastewater generated by the Tata Steel. Then microbial electrosynthesis is another configuration of BS, where instead of generating electricity, what we do, we apply a small amount of electricity to synthesis different chemicals using carbon dioxide as a substrate. So simultaneous carbon sequestration and synthesis of the value-added higher chain carbon compounds are possible here. So the system work like this, that we impose a potential using potential stat, and carbon CO2 is used as a carbon source here, and acetogenic bacteria or other bacteria that we are using with some favorable catalyst, so which will catalyze synthesis of higher chain carbon compound. Scientists have tried with the different configuration, different metals, different metal composition with different imposed potential, and still research is on. I mean, this MES is still the bench scale research even as on today. So scientists have synthesis, format, acetate, ethanol. These are all lab results where we could synthesis acetate, isobutyrate, propionate. Though the yield is still less for if we compare it to commercialization of this, but the efforts are on to optimize the performance, to look at the proper configuration and the system design to enhance this yield of the synthesized chemicals that we can. And also another challenge here is the separation of this compound, because these are all getting synthesized in the mixed condition. How do we separate this? That is another challenge that the MES research presently being facing. And this works with the Coulombic efficiency, higher Coulombic efficiency if we use enriched culture. So 60 to 70% Coulombic efficiency and carbon recovery efficiency of around 18%. So that is good when the gas is admitted in the form of means what we are using here in our lab is the biogas. So the idea here is the biogas which contain nearly 30% of CO2. So if we can utilize that CO2, so that will help in enriching the methane content in the biogas, and the CO2 otherwise which is getting released into atmosphere can be explored for facilitating the different value-added chemicals. So this is what the objective of this ongoing research. A microbial carbon capture cell, as explained, this works with the principle that in the cathodic chamber, instead of active aeration, mechanical aeration, we are going for culturing algae so that the photosynthesis will release oxygen. And these are different aspects. The challenges ahead of the MCC, how to scale it up, the equal challenge as MFC, application of MCC for different type of wastewater. So all wastewater which are suitable for MFC, they are equally treated in the MCC as well. Finding the electrode material is another challenge, both anode as well as cathode, as it is true in case of MFC also. The separator and other challenges. So we carried out some experiment, and then we operated a pilot with the 40-liter capacity. So the results are there also. They are encouraging. So we got the algal yield of 0.62 gram per liter per day in the pilot scale reactor, whereas in the small scale 1 liter scale reactor, we could get up to 0.78 gram per liter per day algal yield. But when we operated the larger scale reactor, apart from electricity generation, the algae produced is also the added advantage, because this harvested algae can further be utilized for biodiesel, for extraction of the bio oil to make biodiesel, and then the remaining for bioethanol production, which is I'm sure is dealt by my other colleagues from India as well as from US. Another interesting observation that we had is the quorum sensing molecules, if we extract from the anaerobic sludge, and that we spike in the algal culture section, that is in the cathodic chamber. So we observe that this spiking of this QSM enhance the biomass productivity, that the algal yield itself has increased by 2.25 times, as well as the lipid content in the algae. So the more algal oil can be obtained by enhancing such spiking such QSM extracted from the anaerobic sludge. So as I said, the addition of some algae in the anodic chamber helps in suppressing methanogen. So this way it will help in enhancing the coulombic efficiency of the MFC, and we got 74% increment in the coulombic efficiency while spiking with some amount of algae in the anodic chamber. Whereas spiking the QSM extract in the cathodic chamber where we are culturing algae, so that way also it will enhance the algal yield. So win-win situation. So both anodic as well as cathodic performance can be enhanced, as well as more algal lipid content, more lipid containing algae can be harvested for the downstream again biofuel production. We coming back to the MFC configuration, we started scaling up. This was in 2008 to 2010. We operated 45-liter microbial fuel cell with half aqueous cathode, half air cathode configuration, using at the bottom ceramic separators, at the top the commercial battery separators. Then we, based on this performance, then we scaled it up to 100 liter. So this is the first 100-liter reactor, MFC base, treating actual septic tank sludge. And this was capable of charging our mobile phones. So the electricity generated from this circuit was adequate enough to charge the mobile. We operated this device for 2 years, and then we further went to scale it up, addressing few other issues related with this. So how to stack up the system to facilitate on-site wastewater treatment, to generate the treated water to meet the quality requirement to be reused back for flushing into the toilets, or use it safely for horticulture purpose, minimize the space requirement. While adopting this bioelectric toilet concept, the space requirement will be minimized, while the smell problem also can be minimized. So because of the anaerobic oxidation of ammonia, there is no smell, which is directly getting converted into nitrogen, as well as anaerobic oxidation of sulfide to elemental sulfur. Even the hydrogen sulfide smell is not there, and the smell problem is being solved. It facilitates reuse and recycling of the water, and thus it will make the water-free toilet. And the electricity generated in this way on site will be utilized for illuminating the toilet premises and the toilet cabin at night, so that the fearless use of the toilet can be encouraged. As most of you are aware, the government of India has built in last few years more than 8 crores of the toilet in the rural area. But those toilets are not connected with the electric grid, and people are reluctant to use such toilets at night. So installation of such bioelectric toilet will make it water-free toilet, because the water that is being generated will be treated immediately and will be available for flushing the toilet. So people have to carry only about a liter of water for satisfying their cleaning needs. This is the performance over the days that we observed over the month in the seasons. Obviously, in the winter season, the current production is marginally slightly lower as compared to the summer. The summer, the temperature is better suitable, but still it is able to produce treated effluent BOD, treated effluent with the BOD of less than about 20 milligram per liter, meeting the needs for reusing back for flushing the toilet. And also the nitrogen and phosphorus are considerably reduced, so that there is no algal growth that will occur in the systems that we are using. This is a photograph of the world largest bioelectric toilet that we have, which employs the MFC-based system. This has a capacity of 1,500 liter. Treating the waste generated from the toilet is coming centrally in the central chamber, where it is getting distributed, half in flowing clockwise direction in the peripheral compartment, half flowing anti-clockwise direction in the peripheral compartment. The similar configuration that we had installed in the another pilot, the NTPC campus and National Thermal Power Corporation campus, Natl, New Delhi. So Greater Noida, that is located. So that also gave more than a year satisfactory performance result, and you can see the illumination of the electricity that is generated at night. Even you can see here on campus what we have at nighttime illumination happening with the electricity generated while treating the wastewater. And then this treated wastewater is stored here, and once in a day we pump it back using the solar power pump to the elevated storage tank. So by doing this, ample amount of water will be always available for flushing the toilet and maintaining cleanliness in the toilet, which is the major hurdle for the toilet in the remote areas. Still, the major cost here is the cost of this vessel, which costed us more than 2 lakhs Indian rupees, so 200,000 Indian rupees. So we tried to minimize it further using only clay-based assembly. So fabricated with the clay cylinder itself. So the cost of 200,000 could be reduced down with this assembly. We are giving similar performance to just 40,000 Indian rupees. So 40,000 Indian rupees we can get the similar performance, but we are compromising with the brittleness. I mean, somebody strikes here, obviously it's a brittle material and will get broken. Whereas this is the robust material, being a FRP-based material with proper protection given to the ceramic separators which we have housed here. So this black portion that you are seeing, these are all 8 by 8 inches ceramic membranes which are mounted here, over which the carbon powder is coated, and carbon felt is being used to be as a current collector, and also it gives some additional cushion for any object that strikes to the this ceramic membrane, so it will not get broken up. So this is what I wanted to share. And at the last, still we have a challenge ahead in scaling up of the system, because the challenges are not coming only from the biology, that is biotechnology. The challenge also lies from the electrical engineering, the polarization loss, and then the electrochemistry, the charge transfer, the Butler-Volmer kinetics that is typically used while modeling the system, and also regular chemical engineering process which all of us are conversant. When we scale up any system, there is bound to be some loss because of the charge transfer, charge limitation, the temperature gradient difference, thermal induced mixing currents, and all those things we have to take it into account while scaling it up. So our experience is that if I am using good conductors at the cathode good conductor cathode material with the appropriate catalyst, which can support high current density of the order of 5 ampere per meter square. So in that case, I can have the single anodic chamber volume nearly about 27 to 28 liter. Still, I can design a system for electrogenesis to dominate. If I go for larger size than this, then in that case, I am opening a scope for methanogens naturally to grow, because my electrical circuit, because of the electrochemical limitations, the current, even if generated by the electrogens, will not be harvested and will not be taken through the circuit, and that will open up the scope for methanogens to grow on anode. And eventually, if they start growing, they will dominate the system. And instead of electrogenesis, it will be getting converted slowly to the methanogenesis. But if I'm not using any catalyst on the electrodes, both anode and cathode, then I should restrict myself to less than 0.5 liter anodic chamber volume. You can understand now what challenge it will have. Even for a single house, a single person generate about 100 liters of the wastewater per day. So if I have to have MFC with only 0.5 liter each, then multiple MFC I should need per person, and also equal distribution of the wastewater in all these small units would be a challenge. So ideally, for where do the future is? Ideally, we should look for development of the electrode based material which can support much higher current densities, one order of magnitude higher than this, so that we can have a 200 or 300 liter size of the anodic chamber to minimize the number of MFCs required for facilitating treatment of this wastewater. So initial results are encouraging. Scientists are working. When we joined this research in 2004, there were only about 30 papers published in this microbial fuel cell domain, and today there are 11,000 papers published addressing different issues of the microbial fuel cell. So knowledge is advancing much faster, whereas being an interdisciplinary area, cooperation from material science, biotechnologies, cooperation from environmental scientists, all those need to link hand together to come up with the properly developed system. This is the photograph of our research scholar receiving this award from the President of India, Dr. Ramnath Kovind. Another set of research scholar receiving award from the Minister, Dr. Harshavardhan. And this is my collaborators as well as the research scholar. And this is my present research scholar group, the young people who do hard work for getting the results in hand and making it possible for me to share the result in front of you. So with this, I will stop, and I hope I maintain my time, and we still have some time to take up any question if you have. So over to you. Thank you very much.
Thank you, sir, for the amazing and highly informative talk. We are open to questions, and we have a question from Manisha Mishra. She wants to know more on biofouling and how silver nanowires are useful in controlling it.
The silver being the biocidal property, the silver nanoparticles are helping to control the biofouling, because the biocidal property of silver is very well known. Have I answered? Hello. Hello, am I audible?
Yes, sir. Yes, sir.
Yeah. So biocidal property of silver is well known. So that is why it is controlling. Can you stop the screen sharing? I am not able to stop it. Share the browse. Okay, now I can do that. It worked. Okay, any other question?
No, sir.
Okay, then, so thank you. And in case if you have any question at a later time, feel free to talk to me. Either me or any of my research scholars will respond to your queries. Thank you.
Thank you, sir. Our next distinguished speaker is Professor Rintu Banerjee, the Head of Agriculture and Food Engineering Department, IIT Kharagpur. She has been associated with this institute since 1993 and has been the recipient of many honors and awards, including Women Scientist Award of the Biotech Research Society of India 2003, Punjab Rao Deshmukh Award for Outstanding Women Scientist in 2012, Rafi Ahmed Kidwai Award for 2013 for outstanding contribution in the field of natural resource management and agricultural engineering, as well as Prem Dureja Endowment Award for outstanding contribution in the area of agriculture in 2016. She also has a patent on the preparation of gallic acid by co-culture and has additionally filed for 14 other patents. She has worked extensively in the fields of enzymology, bioenergy, and protein chemistry, and will demonstrate an innovative, eco-friendly, and sustainable 2G ethanol production method. I request Professor Banerjee to kindly deliver her session. Ma'am, please.
Can you see my screen?
Yes, ma'am.
But why this screen is not coming in a PowerPoint presentation? It is coming in the form of PDF. So it is not coming in the form of slide presentation. Why? I don't know. Ah, yes, I think now it will be coming. Can you see now?
Yes, ma'am. Yes, ma'am.
Yes, thank you, Manali, for your nice introduction, and thank you to my previous speaker, Professor Ghavrekar, who has made my lecture a little easy because he has explained many of the things which is very, very essential to understand. And since morning, what I feel that you have already attended many lectures where this carbon balancing and intermediate and some other such type of terminologies have come, and you have already learned those things, and you already know, many of you know an expert in this field. So it will be little easy for me to tell you on my today's topic, that is on an innovative, eco-friendly and sustainable 2G ethanol production. So this is the topic of my today's lecture, because we are working with UC Berkeley on this 2G ethanol, and as you all know that yes, we are facing a huge challenge on commercialization of 2G ethanol. So many people are claiming many big things, but in reality, the real problems are coming into the picture. So when we are talking about the energy, so the main, if we concentrate on the main driver of this energy, then we can find that starting from the electricity, transportation, to urbanization, each and every sector, it is energy driven, or energy is needed for running those activities. Even the most interesting part is that nowadays we all are talking about GDP and price, and we are just trying to correlate about the income of this farmer, and it is very much related to our GDP. So this GDP driven process is also the energy driven process. So anything and everything, starting from socio-economic aspect to any activities which we want to do in a systematic and smooth manner, that is needed or driven by the energy. If this is the truth, and if we understand that, then from this energy utilization, we can also get very many information which are needed to categorize whether we are developed or still developing country, and that is also based on the energy utilization or energy data which are there for our daily life activities. Now this is a very, very interesting data which I'm just trying to tell you, is that, see, different countries, we are now globalized. So if we now compare ourselves with United States, with China, with other countries like India, China, Europe, Brazil, and so on, we can find that in each country, they have some indicator energy policies, and that indicator energy policies are different from different countries. See here, the gas utilization here in United States is the maximum consumer, followed by renewables. You see here, the renewables are coming under this which country? Why I'm not able to see. This is European, I think. No, Europe is yellow. I think this is which country is. So different country has got different energy consumption. If we see India and if we compare our energy utilization with other countries, we can find that India's maximum energy is coming from coal, and we are very much dependent on the fossil fuel. And that is the reason why I am interested to tell you that since morning we are talking about renewables, but you see the pattern of you see the habits of ours, and you see that how we are going and utilizing our resources, and here we can see that the maximum utilization of energy comes from coal. This is one part of the story. If I come to the other part, you see that National Oceanic and Atmospheric Administration, so NOAA, if I see the atmospheric carbon dioxide level measurement in Mauna Loa Observatory, we can find that there is a straight exponential increase in the carbon dioxide, that parts per billion of carbon dioxide accumulation in the atmosphere. If we see the other part of the story, that see, this is the annual accumulation, this black bar is the annual global carbon dioxide emission from the fossil fuel. See, here in India, we are the maximum utilizer of this coal, fossil fuel. And if we see the carbon dioxide emission from fossil fuel, and the different parts, that different color bars are just seeing the driver of changing between years of fuel, we can find that here also the carbon dioxide emission is taking a very important and significant role. And as the carbon dioxide emission is gradually getting increased, so I was showing the earlier slide up to 2019, but if now I give you the accumulation pattern from 1880 to 2016, you see there is a continuous increase in carbon dioxide in the atmosphere. Now, when this carbon dioxide is increasing and getting accumulated in the atmosphere, so people are not very cautious about this. But when they became cautious, when the temperature of the universe is getting changed, and this is not only the temperature increase in the surroundings, but it has got different impact on our ecosystem, on our environment. So when I'm just talking about the coal utilization, but I'm not at all interested, because if I remember that some of our earlier speakers have told that yes, that that global pattern is showing that how much increase, how much that we are just going for this increase in this fossil fuel in terms of oil utilization, and this is the petroleum product. And I was talking about the fossil fuel, coal, and all this. So gas is, yes, it is a maximum user is US, and then other countries are also getting the indication, and we are seeing the indication of utilization pattern from other countries. So if now I compare the oil utilization, we can find that in coming year 2014 the utilization was 114 billions liters. So in the morning, I think those who were there, you must have heard that when I'm just talking about this particular utilization and energy pattern, it may happen that India occupies 1%, 2% of ethanol demand, but that 2% is in the tune of billions and billions of liters of ethanol. So when I'm just talking about the petroleum product and this utilization, what we can find that here the world market of fuel ethanol is showing maximum when we are talking about the total world. And India, if we see, India occupies only 2% of the world share. And here this is the ethanol utilization pattern. And now when we will be coming to the reality, we will be seeing that till now coal is maximum giving this energy resources, followed by petroleum, and now at present the utilization of biomass is significantly drawing attention, and then followed by natural gases, hydroelectricity, nuclear, and other renewables. So those are gradually getting attention for today's world. And now I think this is the high time where we have to see that the energy consumption in India is rising in a steady state at the rate of 6.5% per annum. And that may be the reason why we are so much concerned about these particular issues, or else we would have not considered till today. And that is the reason why I'm just telling that there are different segments. Let me come to only the transportation sector. Now, when I'm just talking about the transportation sector, and I'm just comparing 2015 and 2030, within this 15 years of time interval, you just see the prediction is telling that 3 times increase in the demand is there. So transportation is only, just you see that how much vehicles are running, and if this is the trend, and if we compare the other sectors with this transportation, then we can find that there is 2-time increase, 2x. But only transportation sector, it is showing 3 times increase in this. And when we are going for little beyond that, and if this trend is going to be maintained, then there is a huge demand. So where from we will be coming? Where from we will be meeting that demand? So this particular situation is compelling us that we have to go for some alternative. So when we are just talking about this alternative, then let us look back a little bit, not very far, just not even 10 years, 5-6 years back. The energy, that petroleum utilization pattern was 114 billion liter. But that prediction is going to be increased to 134.5 billion liter by the year 2024. Today we are now in the end of 2020, not even 4 years, but the demand is so huge. You just see 114 to 134 point, or you can tell approximately 135 billion liters. So if we see the countries and gallons of this global production of this, then different countries and their global percentage is given in this particular chart. Where from we will be bringing that? You see, the other countries like United States, they are producing from corn-based ethanol. Brazil, sugarcane based, corn based, they are producer of this. Then coming to the China. And when Chinese technologies and Chinese things are coming, I don't want to pass any comments, but their things are very, very different from ours. And although I'm just telling that world's utilization pattern, when I showed you that we only occupy 2% of this world ethanol data, but this ethanol, 2% ethanol is also in the tune of billions liter of ethanol. Now, I think in the morning also I have told the concern which one should have, and the scientists of today's era, that what we are thinking and in which way we are trying to address our problem. So if we see the different blending pattern of ethanol with the different petroleum, that means now I'm talking about drop in fuel. That means I'm no more connected to our particular this oil or petroleum product, but now I'm talking about the drop in fuel. So when we are talking about the drop in fuel, Government of India, what they have taken the mandate, they have taken the mandate for 5%, 10% to 20% blending pattern. So the scientists, they were there. So you just see from 2010 to 2030, 31, when this is predictions are there. So you can see that it is also increasing in a logarithmic manner. So the way the transportation sector is utilizing the petroleum product, with that respect only, the ethanol demand is also, the requirement is also getting varied. So when this requirement of this petroleum product is getting increased, so obviously there is a question that where from this ethanol will be coming. And here also this ethanol blending ratio, you just see with 5% to 20%, you see the ethanol demand is also getting increased. So with 5% to 20%, if 5% is this and 20% is this. So when we are just going for billions liter of ethanol, then this is the prediction for India. And when we are talking about the demand and supply of this particular thing, so obviously we are not in a position to analyze ourselves that where we are and how to produce this particular demand, or how to meet this demand, where from it will be coming. So obviously people are thinking for some alternatives. So what are those alternatives? So obviously another liquid biofuel which is coming into the picture is a biodiesel. So when we are talking about this biodiesel and bioethanol, so obviously two things are coming into the picture. If we are honest and if we tell that yes, ethanol for potable ethanol to be used to meet the petroleum product, you just ask yourself how many of you will be coming forward to agree that particular ethanol use for transportation fuel. All of you will be telling that, oh, no, potable ethanol is different and this is transportation fuel, it is different. So you just see this is the portable, and what I'm trying to tell you is that if we see that entire, I think many of us are from biotechnology background, and if we see the demand of this potable ethanol, then we can find that this fermentation technology, this fermentation product is occupying the maximum amount of consumption. Its demand is very high, and this particular potable ethanol, nobody, those who are consuming alcohol, will not going to sacrifice for utilization of this potable ethanol for petroleum substitute or transportation fuel. So here this is the portable, industry and other types, and here I'm just trying to show you that how much alcohol is now being produced for and coming under portable alcohol. So this is the orange bar is the portable alcohol, and it is also getting produced in the tune of billions liters. And if now it is not permissible and if it is not sacrificable, then where from the alternative will be coming? Shall we sit like Corona time? Nobody is moving here and there. So if this is the hardcore truth, then everybody will be telling, no, we are not interested. So we want to go back to our previous lifestyle. So what is the alternative? Alternative is coming as the biodiesel. And if we see the biodiesel, you can see that this biodiesel production is also getting, and its utilization is also getting increased, and this can be a substitute or alternative for this liquid biofuel. So where is our sources? So this is the major question which is coming into the picture. To address this huge demand, now we start analyzing our different resources. What are those resources? So obviously, the bioresource which are there is coming into the mind of the scientific community that can be exploited for this meeting such a huge demand. So when these bioresources are considered, so we are just considering it as direct value or indirect value. So when we are talking about this direct value, we talk about this energy for medicine, building, material, construction, clothing. If we are considering food, we are talking about horticulture. Indirect ecosystem, that is nutrient, recycling, pollination dispersal, seed dispersal, carbon cycle, and so on. So these are the different, very broad classification of the bioresources which are there in this. So here, this primary energy demand and secondary energy demand, I think in the morning you have already heard of the people who have addressed from US, from this University of Berkeley. They are doing different, they are taking the different means to address these biofuel issues. And if we see the global demand of this particular energy, then we can find that major demand comes from China, followed by United States, and India holds the 4th position in world ranking. So this is the different energy, that world's total energy supply. And here the natural gas in 2012, if you see, it used to have this 22.2%. And you see, now the prediction is telling that 2035, it is 22.7%. Just you see that 0.5% change is there. And this 0.5% change has got direct impact on this. Whereas in coal, you see 27.9%. And this coal consumption, I think you must have heard that Germany and other countries, they stopped that coal, taking out this coal. That process has been stopped in many coal mines, and that is the reason why people are going for the alternative these energy sources, and that may be the reason 27.9% 2012 data has been reduced to 27.2%. So here you can see that here this alternative, that coal utilization is reduced. Whereas you see in nuclear 5.5% has got increased to 6.7%. Hydro 7.6% is increased to 8.8%. And in case of solar, you just see 0.3% has been increased to 0.7%. Wind 1.8% has been increased to 3.2%. And that way, the energy demand, that biofuel, has increased from 0.8% to 1.2%. And that is the most interesting part, that non-conventional energy 1.1% has been increased to 2.2%. And that is the attention which I would like to draw to all of you, that yes, this is the change in the pattern of utilization of energy for our daily lives activity. Till now, I was talking about the different liquid fuel, that is bioethanol and biodiesel. But if we see at a glance the different forms, conventional ethanol, advanced ethanol, biobutanol, I think many of the scholars, they have talked on, they address this biobutanol project and this biobutanol production process, biodiesel, green diesel, synthetic gasoline, and renewable biojet. If we see the pattern from 2013 to 2023, what I have already mentioned, I have already discussed in the energy pattern and their utilization process, you will be seeing that the same thing is getting repeated here. And here we are just talking about the different forms of energy which we are interested to use for today's world. So obviously today we are very much interested to concentrate on bioethanol production. Now, bioethanol, there are several issues. There are different people, they are telling that 2G ethanol is economically non-viable. It cannot happen. People are failed. People, they tried and they failed. But nothing is impossible in this world. So we have to, if we are getting the failure results, we have to be very, very constructive in our thinking process, that in which way we should go and address that problem that will be giving us positive result from the negative results. So if we see the pattern of this ethanol from 2018 to 2024. So I'm just giving a very recent data of this ethanol utilization, then you can find that US demand was 55.5 billion liters, and in 2024 it is the demand is 79.6 billion liters. So these are the different, and that too it is the drop in fuel. So that is the major concern of all of us, that in which way we should go for the production of this particular product, which has got a huge market, but we are not successful in producing this in large quantity. So if this is the truth, in India, what are the different sources that can be considered for this? Now you see, in India, now by sitting in India, if we start thinking the country like US, we cannot address our problem in a scientific manner, because in India the major problem of us is our country is thickly populated. So here, when I'll be going for ethanol project, that should not come in between where food versus fuel issues are coming into the picture. So we have to also take care of those issues which are coming, food fodder versus fuel issues. So once we are taking care of these particular issues, because food is a basic need of any living beings. So when we are going for this food requirement, the ethanol is coming, the priority wise, when we are talking about food and ethanol, both are needed. So then first priority will be coming to food, and then only ethanol will be coming. That time people will have that logic that without transportation we can survive, but without food we cannot survive. So if we are just saying, and our country is agricultural based countries, so in our country, if we see what type of agro residues, what type of products can be produced, can be utilized for this particular product process utilization, then we can find that there are different trends from different countries like sugarcane, Brazil, and India. This last in 2018, that energy policies, they have considered this sugarcane as one of the commercial crop for ethanol production. Sugar beet, Europe. Sorghum, India. Cheeseway, New Zealand. Cassava, wheat, China, Canada, Europe. Corn, United States, China, Canada, and so on. Now, if as a biochemist, if we look into this particular system, particular raw material, we can distinctly differentiate each biomass with other, each raw material from one to other. Each biomass is having the distinct characteristics. And when we are just talking about the distinct characteristics, obviously we have to look into the biochemical composition of this particular different biomass, which different country have identified for addressing this particular problem. So when in India we are talking about this particular ethanol issue, obviously we give utmost importance to not to the first generation ethanol production, but we concentrate on 2G ethanol, second generation ethanol. And when we are talking about the second generation ethanol production, we talk about agricultural residues, which include rice straw, corn stubble. We talk about energy crops, which include switch grasses, poplar, and so many other categories which are coming, and woody, paper waste, and municipality solid waste that can be properly utilized for energy generation. Now, obviously, when I'm talking about these agricultural residues, I talk about the lignocelluloses. Now, in India, the entire lignocellulosics are divided, categorized as grazing and non-grazing. So as I have already mentioned you that competition is not food versus fuel, but competition is now lying between food fodder versus fuel. So when food fodder versus fuel is coming into the picture, so obviously these terminologies are coming into the picture. So grazing and non-grazing. In IIT Kharagpur, we started working on non-grazing lignocelluloses. You know, the most important and interesting part of this non-grazing lignocelluloses, when we started working on this non-grazing lignocelluloses, we saw the biochemical composition of this particular non-grazing lignocellulosics are not very different from that of the grazing lignocellulosics. But this non-grazing lignocellulosics either different structurally or it has got some toxin or some biochemical component present within it for which it is not digestible and it is not acceptable to some category of animal which are feeding on that. But rest of the thing, if you are removing that part, it is as good as the grazing lignocelluloses. And when we analyze the non-grazing lignocelluloses, then we came to know, we have seen in the laboratory that the holocelluloses are coming around 60 to 70% of this composition. And that is either we are burning or we are buried under the soil is not the loss of that particular farmer, but it is the national loss. And that may be the reason why we started analyzing it scientifically and to address in which way we have to attack this problem so that this lignocellulosics, out of this lignocellulosics, holocelluloses can be separated out and these holocelluloses can be suitably utilized or converted to the targeted product. So this conversion was going on and these studies were going on and we have standardized the process in the laboratory and we are now telling that it is not only the pure substrate but for billions and billions liters of ethanol production we need not the pure form of the process. Okay, you have plenty of pure substrate, it is well and good. But if you have any shortage of the raw material under any circumstances, you cannot shut down your plant. So in that case, what we have tried, what we have attempted to go for a tailor-made composition so that the plant will not be getting stopped for a single day and it will be running throughout the year as and when it is needed. And that may be the reason why I have mentioned in my title that it is an innovative and sustainable process development. And that is the reason why I have used this sustainability in this particular section. And what I want to tell you is that when we are going for this tailor-made, it is not necessary that every time you have to go for that tailor-made composition, but as and when required, when I have a shortage of a particular major raw material, what should be my substitute? And you will be wondering, and I think most of you will be agreeing with me that our nature has got wide biodiversity. And when I'm talking about one lignocellulosics to other, each of the lignocellulosics have the different nature altogether, their structure, their nature, their releasing pattern, everything is different from each other. And that is the reason why we are very much interested to work with different lignocellulosics and their biochemical composition and their nature of releasing the glucose from the holocellulosic component. So when we were talking about this, now obviously we are talking about different types of composition, which now I would like to tell. You see, rice straw. Rice straw is a plenty, because our country, in our country, rice, in the eastern part of our country, rice is the staple food. And we all, northeast and eastern, we all take rice every day. So if we go to the northern part of our country, their wheat is the major staple food, and they are taking chapatis and all, and that is the wheat-based product. But in eastern part of or southern part of our country, if we see, we can find that millions and billions tons of the straw is getting produced. This straw can be properly utilized. In some part of our country, straw has been used as straw has been used as fodder for cattle. But in many places, what is happening? The straw, after harvesting the paddy, what they are telling, they are either burning that straw and or that is creating a huge environmental pollution that I will be coming. And when such type of products are getting produced, like wheat, johar, sorghum, sweet sorghum, bajra, maize, other cereals, gram, and so many things are there, so many food items are there. When they are taken care of, the harvesting is over, the lignocellulosics which are produced in the tune of tons and tons are the wastage. Either we are just dumping on the ground, and if it contains some toxin, say for example ricinus communis, that castor oil, India holds number 4th in the world. Huge amount of huge acres of land are going for the contract farming. The moment the fruit of this castor fruit is getting isolated, extracted, then the entire plant, either they are getting burnt or buried under the soil. But you know, more than 65 to 70% holocelluloses were there in that lignocellulosics. So that is the reason why I'm telling, it is not 1 kgs or 2 kgs, it is, we are obtaining such biomass in the tune of tons and tons, hundreds and million tons of those byproducts or the extra products we are getting from there. So obviously, when we are considering about this product to be produced and it is to be brought into the factory premises where ethanol will be getting produced, and if I go for state-wise, say for example, Andhra Pradesh to Uttar Pradesh. So if you see different states, you will be finding that at the periphery of 100 kilometers, of the radius where the origin of the product is getting produced 200 kilometer around this particular area where this factory premises for carrying those lignocelluloses from that origin of production to the factory premises, it is adding up 28 to 49 to 31 to 50 dollar of cost per ton of transportation, and that is the extra cost due to the transportation things which are adding up on the initial cost. Now, if the 1 liter petrol cost is increasing by 50 paisa, all of us starts jumping. Petrol product is increased, cost is increased. But when we are talking about this much increase of dollar per ton of lignocellulosics, then you just imagine how much increase in the initial price of that particular biomass is getting increased. So initial price is getting increased. That means we cannot think of our product ethanol in a very cheaper price. But here, this is the bulk requirement. That means our demand is bulk, but price is as much as low possible. We have to reduce the price. Now, when this price is going escalated, then we have to be very, very serious about this end product cost. So, when end product cost is increasing, obviously you cannot imagine to reduce the end product cost if initial raw material cost is getting increased. Then some processing cost will also be added up when we'll be going for the production. So that may be the reason why we are always recommending that this type of industry is not like any steel plant or any such type of industry where you can increase the capacity of your plant, but it should be totally based on the resources available. How much biomass will be available in our premises, and that will be the particular initial requirement for finalizing the site of the plant establishment, and it should be decentralized manner. It should not be in a centralized where the initial cost has to be taken care of. And this is the reason why I'm just telling that here in India, we have studied this and we have come to this conclusion that it cannot be. It cannot be very far from the origin of production. So this is the bagasse. I'm talking about bagasse. But when I'm talking about the burning of rice straw, I am just showing that how much of pollutants are getting released in the atmosphere, and that are making our atmosphere very, very polluted. And that is the reason why I'm just telling that quantitative manner, if we see 1 ton rice straw is producing 199 kgs of particulate matter, ash, 3 kgs of particulate matter, 2 kgs of SO2, 60 kgs of carbon monoxide, and 1460 kgs of carbon dioxide, and that is getting released in the atmosphere. So if this is the happenings of today's world, then how one can go for the huge production, that millions and billions liter of this ethanol. So this biofuel, when we are just talking about, we now want to say that it will not be a pure bioethanol production, but let us have a look on what are the other forms of biofuel which are available and that can be attempted or exploited for this. So bioethanol, biobutanol, biodiesel, these are the 3 distinct liquid fuels. While coming to this gaseous fuel, what we can see biomethane, biohydrogen, syngas, and the mixture of biohydrogen. That is the other side of the story. So, in which way we will have to, because now I have addressed very many issues which are there for commercialization of this particular bioethanol, 2G ethanol. So when we are just talking about commercial scale, that means we cannot think of one product. We have to go for the integrated biorefinery approaches. So now in a nutshell, I can tell that after so much of talking, I can tell that this is the hardcore reality of today's India. This is the demand and this is the supply. So there is no correlation between the supply and demand. And that is the major concern of us. Now, if this is the truth, then let us come to the science of 2G ethanol production. Now, when we are talking about the science of 2G ethanol, I have told that cellulose and hemicelluloses, these are the hardcore biomolecules for which we are looking for. We are selecting the biomass in such a way that where these two molecules will be present in maximum amount. And this lignin, these are acting as a village for us. So in our in the earlier in the afternoon session, I think Mr. Kundu has already discussed, and Mr. Shubhodip Banerjee, he has discussed the different physico-chemical pretreatment method which has been used for the pretreatment of this particular biomass. Now I'm just talking in the first half. I think you must have heard of Lumit, where he was talking about first generation, second generation, third and fourth generation biofuel. So here I want to only tell that we are talking about the 2G ethanol that comes under the second generation, and we may club up our second generation with the third generation, and we may go to Professor Ghandekar for our microbial fuel cell production. So we will be going for an integrated approach for 2G ethanol production. And my collaborator in UC Berkeley, they are going for this fourth generation. And here my co-PI, Professor Amit Ghosh, is also trying to do on fourth generation biofuel, and their major attempt is to go for the engineering the microbes. So here, if we see the major bottleneck, then we are talking in the morning. I think many of you have heard of the Aindrila. Dr. Aindrila was talking about the precious carbon molecules. So what I'm just telling, that here we are very much concerned about the precious sugar molecules, sugar moieties. A single molecule of sugar, if it is getting lost from the system, it is a loss for us. We cannot achieve maximum yield by losing our sugar moieties from the system, and that may be the reason we have to go for the selection of process in such a way that when we will be going for the utilization of the process, there should not be any intermediate production, and that intermediate should not be at the cost of utilization of sugar moieties for ethanol generation. And that may be the reason why we have jotted down these many points, where starting from furfuryl, hydroxymethyl furfuryl, pentoses, hexoses, and the strain which will be going for high percentage of ethanol production, should have that much tolerance to withstand that high concentration of ethanol in their surroundings. And that ethanol should not affect on the yeast, who is the actual driver for converting this sugar to ethanol. And these are the major concerns which was noticed, which were taken into very serious concern of ours when we started doing this 2G ethanol production utilizing the biomass. These are the different biochemical, physicochemical processes which Shubhadeep has already addressed in details. But in today's presentation, I will be concentrating on biological process. So biological process, when we are just talking, I will be talking on different enzymes. So Aindrila, I think you must have heard her that she was talking about on only cellulase. But here in this particular project, what we have done is that from first step to last step, we have not used any chemicals. Everything is bio-based process. And here, as a result, what we have gone for is the ligninase or the lacase or lignin peroxidase and manganese peroxidase, this type of lignin hydrolyzing enzymes which are used for removal of the barrier molecule, the most robust molecule in lignocellulosics. And we very easily, we remove this that lignin through biological pretreatment method. And we started comparing our results with the published results through physical, chemical, and physicochemical processes. So lacase is a wonderful and miraculous molecules which act on lignocellulosics, which act on lignin, and while classifying this lacase, we have categorized this lacase as blue lacase, yellow lacase, and white lacase. But when we started working, we found that the mode of action is a bit different. And when we have seen this lacase and their mode of action, we found that some are mediator dependent and some are non-mediator dependent lacase molecules, and that is resulting in different forms of the end product, which are not at all toxic to the hydrolytic process. And that is the reason we started working on different sources of lacases, fungi, bacteria, plants, and even if on insect gut, these lacases are found, and we have gone for the finalization of the strategy, because our strategy is very different from the conventional practices what people are adopting, are using for 2G ethanol production. And here we have used all the microbes and the enzymes for this. As a result, what we have seen that our water requirement for this ethanol production has drastically got reduced, and that water which is getting utilized and produced as byproduct is once again recycled back to the mainstream by simple filtration and just water treatment method. And that is the reason why I'm just telling that environment is automatically taken care of with this process. As I had told you earlier that our selection was such that no hydroxymethyl furfural or furfural production was there. So obviously we were not using any chemicals for our process. Our system I have told is a biology based process, enzyme mediated process. So once we are using the enzymes, and these enzymes function extremely under mild environmental condition, no chemicals we have used for this process, so obviously it is not having any high energy intensive process. So once the severity is coming into the picture, so our process comes under the no severity. So neither low severity or high severity, our process is coming under no severity of these chemicals or the extreme condition. So obviously the yield of our process has increased. At IIT Kharagpur, we are working with different types of raw materials, different types of biomass, and I'm happy to share with you all is that each biomass is having different characters. One is totally different from other. By working with one, you cannot decide that yes, the same process can be applied on the other. And that may be the reason more than 12, 13 students are working their biomasses, different types of biomasses thoroughly, and they are doing it for their PhD degree. And each biomass is different from that of others, including their mode of action. This is the laboratory where we have set up our pilot plant facilities, and this 2G ethanol program is going on at Pilkesina Center for Bioenergy. So our unique development, what I want to tell you is that is the enzyme mediated process, and we have gone for the different types of lactases. Some are blue, some are yellow, some are unidentified lactase. Still work is going on, and each of the lactases are also different from each other, and we have published a number of papers from in different journals where their characteristics, their behavior, and their mode of actions are have been taken care of and published. So these lactases are the different enzymes and its behavior we have seen. And one very interesting part which we have observed, that for pretreatment method, it is not necessary that you have to go for 100% lignin removal. So that is another observation which we had, and that is the reason why I told that when we have gone for this holocelluloses utilization, we have not lost a single sugar moieties. As a result, we have got a very sharp increase in our ethanol percentage. And then we optimize the processes, and we have gone for the scaling up process, and we have gone for the biochemical analysis of each molecules. After each phase, thorough scientific studies have been done with the different types of this biomass and the mixture component for tailor-made composition. We have gone for the XRD to see the percent crystallinity of the celluloses, and we have also gone for other parameters which are there, say for example pore size and volume before and after this particular treatment has been done, and each of the biomass have differently behaved from each other, and that is the reason what we have come. And I think in the presentation of Mr. Kundu, you have seen that he was talking about different type of processes, starting from that separate hydrolysis and fermentation to the separate the simultaneous saccharification and co-fermentation. So different types of combination, permutations and combinations were studied, and each biomass has given different types of results under different fermentation condition. Then based on this particular data, the earlier data, we have gone for the pilot plant studies, and you'll be knowing that you'll be happy to know that after each run with different types of biomasses, we have got different level of results, and these are the different conditions which we have adopted for our system. These are the different conditions which we have adopted for our system. This is the real pilot plant at IIT Kharagpur Pikesina Center, and you will be happy to know that Aindrila was telling that 3 pot to 2 pots, and I'm just telling that we have brought 3 pot experiment to 1 pot experiment, and in a single pot we started the working with the this enzymatic method, pre-treatment, hydrolysis and fermentation together, and we are successful in completing the run within 24 hours of processing time, where the ethanol percentage is varying from substrate to substrate, biomass to biomass, and maximum ethanol production we have got with Khan's grass, where we have reached up to 7.5 to 8% volume by volume ethanol. And these are the pilot plant attachment for this particular our Pikesina center. And after that, when this biomass is this bioethanol is produced, ethanol is a liquid fuel. The residual solid which were there, because since morning I think you have got the carbon balancing idea, so we have gone for this methane generation, and we have got a huge quantity of methane generation. And after getting the methane, you see the blue flame of methane which are there. So after methane is a gaseous product. So after methane is getting produced, the solid biomass which is left over is further got valorized, and we have gone for bio-manure production. And one PhD student has completed her PhD on this, and then we have gone for the NPK enrichment in that biomanure, and we have gone for different soil application and with different types of crop system we have done. And this is the overall production and the scheme what I'm proposing, where I have taken the 2G and mixture of 2G and 3G. Some students are working with biodiesel, some are working with bioethanol, and I have clubbed both the things together, and we are just seeing that, yes, some people they claim that they are talking about carbon neutral. Sometimes we are talking about carbon positive, but what I'm claiming here is the carbon negative process product development through this integrated manner. And here the entire picture is telling that this is a carbon negative process which we have developed, and each process, each product is fetching revenue and making the process economically viable. And with this, I would like to tell that these are the patentable work. We have done this work with the help of and my different students who are my strength, and they have got their either degree or they are still associated with me, and we have developed this process for 2G ethanol production. Thank you very much for your patiently hearing. If you have any question, you can ask me. I will be happy to share that. Thank you very much.
Thank you, ma'am, for the very inspiring talk. We have a question by Mr. Prabhat Swain. What is the current potential of bioethanol production in India right now?
Now still it is under trial level, and no industry is now producing it in large quantity. That is the present scenario. So that is the reason why I'm just telling that yes, the present scenario is not at all attractive. So we have to do a lot. We have to do a lot for this particular. So here still we are in the trial level. No commercial production unit has come.
Thank you, ma'am. We are open to more questions if anyone would want to ask anything else. Uh, Thank you, ma'am.
Thank you.
So-
Thank you very much. But I'm not able to cross. How to cross this? It is, I'm not able to. I don't know what happened. I don't know what happened.
You will probably have to stop sharing the screen.
Is it? But
Yes, ma'am.
I have already crossed and now I'm not seeing this.
We can still see your screen. I think you'll have to stop sharing your screen.
But where to? I don't know.
Let's introduce the next speaker.
Yes.
Ah.
Start.
Yes, ma'am. The next talk will be delivered by Mr. Lohit Srinivas, PhD student at IIT Kharagpur under the supervision of Professor Aindrila Mukhopadhyay. He will speak on a closed loop process for biodiesel production from lipids of Aspergillus awamori utilizing lacase treated waste liquor of Micinus communis. Mr. Srinivas, please.
Hi, greetings to all. Am I audible?
Yes.
Greetings to all. I am Gujjala Lohit Kumar Srinivas. I am a PhD scholar working under the guidance of Professor Rintu Banerjee and Professor Tapas Bandyopadhyay in Advanced Technology Development Center of IIT Kharagpur. And today I am going to present on the topic a closed loop process for biodiesel production from lipids of Aspergillus awamori utilizing lacase treated waste liquor of Micinus. So, to begin with, biodiesel is a renewable and a sustainable alternative to petrodiesel because of these main reasons. Depletion of resources with the current rate of utilization of fossil fuels, you can see that initially we will be oil will be depleted by the year 2050, followed by gas in the year 2060. And coal will be the last one to be depleted by the year 2100, provided all the current rate of utilization is maintained. The second major driver for utilization of biodiesel is soaring energy demand. And within the spectrum of fuels, if we see, then the proportion of diesel and jet fuel with respect to the gasoline is nearly twice as per the estimate in the year 2020. And again, there is a government mandate, National Policy on Biofuels 2018, which suggests that 5% blending has to be done for biodiesel with the petrodiesel. So these are the main drivers, and some others are like the fluctuation in the prices of fossil fuels, which is a major import from Middle East countries. If we are able to develop an indigenous process, then we can tackle those kind of issues. And even the environmental concerns, the petrol-based diesel leads to deleterious environmental emissions, which can be reduced by using biodiesel. As you can see that nearly 78% carbon dioxide can be reduced, 48% carbon monoxide, 47% particulate matter, and 6% hydrocarbons, but there will be slight increase in the NOx. Not able to change the slides. India consumes almost 5 times more diesel fuel than gasoline, and Hence, the demand for diesel is more than that of gasoline, and by utilization of biodiesel in this respect will be more beneficial. And because of these reasons, it is renewable in nature, it is non-toxic and biodegradable, and its exhaust emissions are cleaner in comparison to fossil fuels. No vehicle modifications are required if we blend it at any ratio with the petrol diesel. Biodiesel further can be divided into three generations based on the feedstocks utilized for the production. First, second, and third. For first generation, we basically will be utilizing edible oils like soybean oil, groundnut oil, sunflower oil, sesame oil, neem oil, rice bran oil, and palm oil. And for the second generation biodiesel, we have to will be using non-edible tree-based oils. So basically, the first generation biodiesel, there is a issue of food versus fuel controversy, and hence, in order to tackle that issue, the progression of research switched to second generation by utilizing non-edible tree-based oils. Still, there is an issue with the second generation oil. Oil is that huge acreage requirement and large growth cycles, and hence, at the adoption of third generation of biodiesel, which utilizes lipids from oleaginous or microorganisms such as oleaginous fungus, yeast, and microalgae. Further, biodiesel can also be divided into by the mode of production of biodiesel, such as fatty acid methyl ester based biodiesel, which is basically a product of the transesterification reaction. Green diesel, which is basically catalytic hydroprocessing of vegetable oils and fats, and Fischer-Tropsch diesel, which is basically resulting from the Fischer-Tropsch process, and white diesel is catalytic hydrotreatment of waste cooking oil production. So if we compare the different generations of biodiesel, then edible vegetable oils, they lead to food versus fuel dilemma, have high production cost because of the high cost of raw materials, and huge land is required. Hence, the natural progression to non-edible tree-based oils. Again, we have longer incubation time and huge acreage requirement. And therefore, the adoption of third generation biodiesel, which have shorter incubation time, there is an ease for scale up, and the lipid profile is similar to that of vegetable oils. These are the unit operations which are basically required for biodiesel production. Cultivation of oleaginous microbes, harvesting of biomass, cell disruption, lipid extraction, transesterification, and purification of biodiesel. If we go into the details of these unit operations, then we can see that filamentous fungus is a very difficult organism to grow in large quantities. Therefore, special type of bioreactors are required. We will start with the simplest, the batch system. We have to consider that filamentous fungus depends upon the depending upon the genus and species, the morphology will change, and hence we cannot grow all kind of filamentous fungus in batch reactor having mechanical stirred Russian blade impellers. So we have to think about airlift reactors, which are very less energy intensive, and the mixing is basically done through gas bubbling. And we can also use biofilm reactors such as tray bioreactor with stacked trays by recycling the nutrient media. Also, we can use metallic support reactors where with recycling of nutrient media, and the biomass will be basically growing on the metallic support. So the next unit operation is the harvesting of fungal biomass. So in large scale, harvesting of fungal biomass can be basically done using either hydraulic presses like tincture press, which basically is a combination of two coaxial cylinders, the inner one containing perforations, and the biomass basically is packed inside the filter cloth, and the hydraulic press is operated, and the final dewatered biomass is entrapped within the filter cloth, and hence we can harvest the biomass. And if we want a continuous operation, then we have to use decanter centrifuge kind of unit operations like equipments, where there will be continuous loading of biomass, and there will be continuous separation of solid residue. Then the major step is lipid extraction. So lipid extraction is basically done by combination of solvents like unary solvents also you can use like hexane and all, but binary solvents are more useful like combination of chloroform, methanol, etc. and we cannot use those solvents alone for high efficiency. So we have to use some process intensification techniques like ultrasonication, microwave extraction, oxide extraction, ball milling, electroporation, and expeller press. In ultrasonication technique, basically cavitation and acoustic streaming are the two major reasons why they are able to disrupt the cell wall and hence are responsible for extracting lipid out of the cell. And then using the solvents, we can extract the lipids into the organic layer. For it, the efficiency is high, but there is high initial investment and maintenance cost. Even the energy is high as both for sonication. During sonication, the heat is generated. So even for cooling, we need some energy. So energy requirement or energy footprint with respect to ultrasonication based lipid extraction is high. So even for microwave extraction technique, what happens is the rapidly oscillating electric fields generates microwaves, which leads to generation of water vapor, which disrupts the cell from within, and hence lipid is leached out of the system. And here also the efficiency is high, and the cost also is high. Initial investment as well as the maintenance is high, and energy requirement here also we have to use energy both for like cooling as well as disrupting the cell. In oxalate extraction, the basically we are refluxing the biomass placed in a thimble with the solvent. Here the efficiency is moderate; it's not that high, and it requires long operation times. And cost is moderate but it's very difficult to scale up. Energy requirement is moderate to high. In case of ball milling, it basically uses mechanical method for disruption of cells, and efficiency is moderate. It is not that costly, but the energy requirement is high. In case of electroporation technique, basically we will be using electric field to disrupt the cell wall. Efficiency is high and with high initial investment and cost investment and operational expenditure will be low. Even the energy requirement will be low in this. In case of expeller press, it also applies high mechanical pressure for crushing and breaking of the cells with low to moderate efficiency, high cost, and high energy requirement. So with these process intensification steps, we have to use solvents for extracting the lipids. So traditionally, we'll be using poles and glee and dye, basically a combination of chloroform and methanol in different ratios. In addition to that, there are newer age solvents are bio-derived supercritical fluids and ionic liquids. So basically, some of the bio-derived solvents are terpenes like limonene, pinene, cymene, supercritical fluids like supercritical carbon dioxide, eco-friendly solvents like bioethanol, dimethyl carbonate, and one of the specialty of dimethyl carbonate is if you are using dimethyl carbonate, you will be getting glycerol-free biodiesel, as the glycerol also is integrated with the fuel. And cyclopentyl methyl ether, water, ethyl acetate, ethyl lactate, methyl trihydrofuran, some petroleum-based alternatives like butane, even ionic liquids like polonium ethanoate and dipyritic solvents like choline chloride, proline, and malic acid in 1:1:1 molar ratio can be utilized. These are the newer age solvents. Even enzyme-based methods also are used, utilizing cellulase, mannase, and xylanase. And osmotic pressure-based methods utilize surfactants like CTAB and for extraction of lipids. So if we go deep into the lipid extraction using bio-derived solvents, for example, terpene, so basically it extracts the lipid, and then the main major advantage with using terpene is we can using Clevenger distillation apparatus we can separate the solvent and it can be reused for the consequent steps. So major advantages are it is the solvent is derived naturally, it is efficient, eco-friendly process, and it possesses degreaser properties. It's easy lipid extraction. Even the solvent is having the toxicity footprint is low. It is biodegradable and it is renewable in nature. Disadvantages are meager terpene supply and because of very difficulty in its extraction, and very few studies have been conducted on its large scale application. Then supercritical fluid technology. So carbon dioxide in supercritical state can be utilized for extraction of lipids. So the major advantages are high selectivity due to the flexibility of changing pressure and temperature. So once supercritical carbon dioxide extracts lipid, by changing the pressure and temperature, we can remove lipids from the solvent. And even this carbon dioxide can be recycled back. So hence there is no greenhouse gas emission from this process. But the disadvantage is the high equipment and operation. Ionic liquids are non-aqueous salts which contains both anions and cations, and the major advantage is they can remain in the form in liquid state for for a wide range of temperatures. For example, 0 to 140 degrees centigrade depends upon the ionic liquids, and they are very highly specific and less hazardous, non-flammable, and single ionic liquids can serve the purpose of lipid extraction, and there is no requirement of any binary solvents. But the disadvantages is high cost, and very little amount of scaling up studies have been conducted with ionic liquids. So still some work has to be. Some newer techniques are utilization of switchable solvents. So basically, switchable solvents are special type of solvents which can be reversibly switched between hydrophobic and hydrophilic state. For example, some tertiary amines which are hydrophobic and hence are immiscible in water. But if we introduce carbon dioxide into the system, then they become miscible in water because of the formation of bicarbonate. And again, if we purge nitrogen into the system to strip carbon dioxide out of the system, then we can recover back the entire solvent system. So the advantages are its suitability for multi-step lipid extraction. There is no need for replacement of solvent in the next step. Easily, it can be switched by purging nitrogen, and recycling can be done for several extractions. The disadvantage is the technical viability. In this case, also, it is in a very nascent stage, and technical viability is yet to be confirmed. One of the subgroups of ionic liquids is deep eutectic solvents, which basically are a combination of hydrogen bond acceptors and donors like chlorine, chloride, and urea, etc. With fungal biomass, if we use deep eutectic solvents, then we can, with high extraction efficiency, it can extract liquids. So one of the major advantages is fluid systems. So it occurs naturally, and hence it's safe and inexpensive. It is biodegradable in nature and low cost synthesis and low volatility and wide polarity. So still, but it has a disadvantage like the other previous ones. Like lot of studies have to be conducted for utilizing it at large. So going into the transesterification types, it can be classified into homogeneous and heterogeneous. So utilization of acid base, and in heterogeneous also depend based on acid base and ion exchange regimes. And these are all so in case of there are also enzymatic catalysts like lipases, which are triacyl glycerol acyl hydrolases, which can also be used as bio. So in acid catalyst transesterification, basically we'll be using Lewis acids and carboxylates as catalysts. Basically, acid catalyzation is considered to be pre-treatment to the base catalyzed transesterification, because it is not sensitive to the concentration of free fatty acids. So basically, it will perform esterification as well as transesterification, but its transesterification efficiency is poorer in comparison to base catalyzed transesterification. And hence, in combined systems, it is used prior to base catalysis. Major advantages is it's relatively insensitive to free fatty acids and less energy is required. Disadvantages is it requires higher temperature, and biodiesel has more amount of free glycerol. These are the most commonly used catalysts. Sodium hydroxide, potassium hydroxide, and sodium methoxides are these are the main base catalyzed base which are used for catalysis of transistor. Advantages are fast process and high efficiency, and low temperature and pressure, and relatively cheap. Disadvantages are very sensitive to free fatty acids because of the formation of soap, and hence their difficulty in purification of oil. So combining both acid and base, so we can develop heterogeneous catalysts. A lot of work has been done. heterogeneous catalyst possess both dual acidic and basic sites, and simultaneously we can perform esterification as well as trans-esterification. Some examples are lithium calcium oxide and sulfate and titanium. So the three-step process: adsorption onto the acid-base catalytic sites, nucleophilic attack, as well as desorption. So by using heterogeneous catalysts, the major advantage is we can recover the catalyst much easily because of the change in the phase of the reactants and the catalyst. Then biocatalysts, lipases are the major biocatalysts. These are triacyl glycerol acyl hydrolysis. In free form, they have lower activity, lower stability, and difficult to recycle. So one of the steps to increase these attributes is to immobilize it with some solid supports like sealite, silica gel, inorganic nanoparticles, etc. And by doing so, the efficiency for trans-esterification and even in some other applications increase. So the final unit operation for biodiesel production is the purification of the biodiesel. So purification of the biodiesel after separation of glycerol from the mixture of glycerol and FAME, still some impurities are left over, so which have to be removed so that the biodiesel can be used with high efficiency in blend with the petrodiesel. So four major steps are there, four major options are there, like equilibrium based, like using distillation or extraction; affinity based, like using adsorption or ion exchange; membrane based or reaction based. So one of the major bottlenecks of biodiesel production is the high cost of raw materials. So in order to tackle that, we have to use inexpensive industrial residues. So for example, lignocellulosic hydrolysates, which is a byproduct of the biorefinery process. If, for example, 2G bioethanol production, the first step is physical pre-treatment. Is a pre-treatment, that is the removal of lignin. So conventionally, it is done using acids, which leads to the production of a huge amount of spent liquor, which is rich in sugars, and hence the sugar reserve is reduced. The sources are reduced, and this spent liquor, rich in sugars, and also some dehydrated sugars like hydroxymethyl furfural and furfural. This stream can be utilized for lipid accumulation by oleaginous microbes. But these hydroxymethyl furfural and furfural impede the fermentation step. Hence, the work that I'm going to show, we had used enzymatic process for delignification, which did not lead to any hydroxymethyl furfural or furfural production, and hence the leachate obtained after lacase-mediated delignification of resinous communis, that is a lignocellulosic biomass, was utilized for lipid production. And even the crude glycerol, which is a byproduct of the biodiesel production process, can also be utilized for biodiesel. By doing so, basically, we are developing a closed loop process, that is utilization of the waste streams or the side streams to add further value to the process. So this is the schematic of the work that we have conducted in PKCNS Center for Bioenergy. We have scaled it up to 40 liters production tank. We have basically utilized lacus-treated waste liquor of resinous communis, and we have performed optimization of the media and the reaction conditions for lab scale process, and then we scale it up to pilot scale. And in this process, we had utilized lipase-mediated trans-esterification for biodiesel. So the enzyme-treated biomass leachate of resinous communis was slightly acidic in nature, which favors the growth of filamentous fungi, with a reducing sugar content of 3.7 gram per liter, which was majorly comprised with pentose sugars. However, the presence of xylose transporter, xylose reductase, and xylitol dehydrogenase in Aspergillus avameri makes it amenable to utilize the C5 sugars. Moreover, the C by N molar ratio was estimated to be 132.45. That means it shows the nitrogen stress which is basically required for lipid accumulation. And the total phenolic content of this leachate was estimated to be 609 microgram gallic acid equivalent per milliliter. And GCMS analysis of the broth was done, and the major signature compounds were estimated to be organic acids like benzoic acid and some aldehydes such as 3-bromo-5-ethoxy-4-hydroxybenzaldehyde. these intermediates stimulate the growth of fungi. Basically, this can be utilized as a media for culturing oleaginous microbes. Further, we have studied the process, like change in the profile of different parameters as a function of time, and we had observed that on second day of incubation, the nitrogen gets completely exhausted, after which the carbon source is mostly channelized towards lipid production, and the carbon source gets exhausted on fourth day of incubation. Beyond which, there is a slight dip in the biomass, maybe because of utilization of carbohydrate sources or liquid sources for its own maintenance. A lipid titer of 0.5 gram per liter was obtained with a yield of 140 mg per gram of reducing sugar. So, further, the fatty acid composition of the lipids was estimated using GCMS analysis, and it was majorly comprising of palmitic acid, stearic acid, linoleic acid, and oleic acid. The ensuing biodiesel was estimated for oxidative stability and higher heating value, which was estimated to be 9.17 ounce, and higher heating value of nearly 40 megajoule per kg, at a cold filter plugging point of 12.61 degrees centigrade. As we can see from this table, that most of the parameters are within the standards as prescribed by Bureau of Indian Standards, ASTM, and European Union. But for a cold filter plugging point, it is amenable for application in summer season, but not for winter. So further, we studied the like the best lipid extraction technique in the spectrum of ultrasonic assisted extraction, micro assisted extraction, surfactant assisted extraction, and Soxhlet extraction, out of which ultrasonication assisted extraction led to maximum lipid content, and with a processing time of 15 minutes, amplitude 70%, cutoff temperature of 50 degrees centigrade, and chloroform to methanol 2:1 volume to volume ratio, and methanol was observed to be the best style, and the maximum lipid content of 38% weight by weight was observed. Further, the mass balance analysis was conducted where 1 liter of enzyme treated biomass leachate containing 3.77 gram per gram reducing sugar led to 0.46 gram of biodiesel, and two side streams such as lipid free biomass 1.02 gram and glycerol 0. We had also conducted studies with crude glycerol. This glycerol was provided by Bestfill Private Limited, Australia. So basically, this is a byproduct of rice bran oil-based transesterification process, and the glycerol contained 86% free glycerol content, and we utilized we made aspergillus homoly to utilize the glycerol, and we observed a maximum of 127 mg lipid yield per gram of free glycerol utilized. And again, here also the fatty acid from here, strikingly the oxidative stability enhanced 27.1 hours with a higher heating value of 40 megajoule per kg and cold filter plugging point of 6.48. So here we can say that the cold filter plugging point is nearly at par with the applications in the wind. And the mass flow analysis suggests that from 15 gram of crude diesel we could obtain nearly 1.45 gram of biodiesel, and the side streams the liquid biomass 2.9 gram and glycerol 0.4 gram. To summarize the work that we have conducted in PKCNA Center on biodiesel production, so enzyme treated biomass leachate was observed to be a potential source with 140 mg lipids per gram of reducing sugar utilized, and crude glycerol with crude glycerol we could achieve 127 mg lipids per gram of free glycerol utilized. And the fatty acid content of the aspergillus homoly revealed the dominance of oleic, stearic, palmitic, and linoleic acid, and ultrasonic sonication assisted extraction led to the maximum of 38% lipid content, and out of the different acyl acceptors, methanol led to maximum of 90% flame conversion, and the quality of the biodiesel, ensuing biodiesel, is in conformance with the Bureau of Indian Standards, ASTM, and European. So these are some of the references which I have referred while preparing the presentation. I would like to thank Rintu ma'am for allowing me to presentation.
Thank you, Mr. Srinivas, for the talk. We are open to questions.
Lohit, a very interesting talk. So what kind of lacase producing organism you have used? How that is used to actually delignify biomass?
Yes. Pleurotus species.
Rotor species. How do you optimize the production to improve the enzyme in
That is already optimized in the lab. I have just utilized the enzyme that was provided and then I carried out.
how much you got for the production level of enzyme?
Sir, my work started out with the enzyme. So there were some seniors and some colleagues who are working with the enzyme production. I just used the enzyme for this.
You have to purify the enzyme, or it was
No, crude enzyme.
crude? Because when the fungus is producing the enzyme, so it may be contaminated with the media as well, right? Or you have to separate it out.
No, with the crude enzyme, I got this result. So it was giving good results. So I didn't think of purification. It's not required.
The purification is not required.
No.
And you mentioned about the co-culture, right? The co-culture of two organisms.
Not in this presentation. Not in this.
Not in this.
Excuse me, can I ask a question?
Yeah.
Yes.
Yeah, you were talking about fungal algal combined system. So why are you not opting for like fungal mediated bioharvesting of algal biomass?
That I have done, but I have not shown in this presentation. So
Okay.
yeah,
Thank you.
yeah.
Okay, thank you, Lohit. Wonderful work. All the best.
Thank you.
We have another question if we have time.
Yeah.
So this question is by Mr. Prabhat Swine. What is the temperature of ionic liquids that you are using in this study?
No, I did not use ionic liquids. I did not use ionic liquids. I used chloroform and methanol for extraction of lipids. Ultrasonic assisted chloroform methanol. So that was just the literature review part. In my study, I used chloroform and methanol with ultrasonication.
Thank you, Mr. Srinivas. We'll move on. So now I would request Dr. Amit Ghosh to kindly introduce our next speaker, Dr. Nathan Hillson from JBEI, Berkeley National Laboratory.
So our next speaker is Dr. Nathan Hillson from Bioenergy Institute, Berkeley National Laboratory. Dr. Hillson got his PhD degree from Harvard Medical School, and then immediately after that he did his postdoctoral work in Stanford University, and then he started his own group in Lawrence Berkeley Lab. He has been working in private sector as well as in public sector. For example, he is the co-founder and chief scientific officer in Teslagen Biotechnologies in California, and as a head of biodesign within the biological systems and engineering division, Dr. Nathan Hillson lead scientist and engineer within Lawrence Berkeley National Laboratory, whose domain expertise spans synthetic biology, metabolic engineering, microbiology, microbial community, and software engineering and laboratory automation engineering. As overall principal investigator of the US DOE Agile Country, Dr. Hillson leads a larger group of scientists and engineers who span across 7 US DOE national labs toward the development of a public infrastructure that enables the private sector to reduce the cost and accelerate bioprocess commercialization timelines. And this infrastructure complementary discovery engines by enabling the discovery the pathway to be more quickly and reliably optimized and scaled. The efforts are supported by DOE-funded entities, and then including the DOE Agile Biocountry, DOE Joint Bioenergy Institute, DOE Joint Genome Institute, as well as industry-sponsored collaboration he is having. he is mainly developed many interesting software and laboratory automation devices that accelerate and engineering of the microbes become easier. And today he will be talking about many of the softwares he has developed. I personally benefited from DIVA J5 when I started my postdoctoral fellowship in Berkeley lab, and still I am following his using his software and really benefited. And today he will be talking about DIVA EDD ART, and that is software spanning the design, build, test, launch cycle. I welcome Nathan to give his talk, and Nathan, the stage is yours. Welcome.
Thank you very much, Professor Ghosh, for that nice introduction. Good to see you again. I'm glad to join you all this evening, your time, or California. It's pretty early for Garima and I. But I'd like to thank Professor Bioenergy and Professor Amit Ghosh for the invitation to participate, and the Spark project for supporting the workshop. I'm probably going to present some slides just as introductory remarks. And if there is still time, I would like to provide some demonstrations of the software that you all could use and potentially benefit from. So I'll go ahead and do that. So let me start sharing my screen. And let's see. Go into presenter mode. All right, I believe you should be able to see my screen now.
Yes.
All right, perfect. So I think what I'll probably do is, for the first few slides, I would like to provide an introduction to the United States Department of Energy's Agile Biofoundry. This is a sister project to the Joint Bioenergy Institute, which you may have heard from Aindrila Mukhopadhyay, as well as Deepika Banerjee this morning, your time, or very late last night, our time. So this is a slightly different project. So I'll provide a couple of slides of introduction just for context as to where these tools are coming from. So the Agile Biofoundry, the overall goal of the Agile Biofoundry is to really enable the private sector, so commercial biorefineries, to accelerate how fast they can develop bioprocesses. And the outcomes of our project will be to have the development and deployment of technologies that really enable these commercial biomanufacturing approaches in both kind of new and established industrial microbial hosts. And we are a $20 million US per year public infrastructure investment that really does help the private sector. So the way that we talk about ourselves is generally through an analogy with the transportation sector. So if you go to different large cities across the world, generally what you'll see is a combination of public transportation and private transportation. So shown here in darker blue lines might be public infrastructure, including things like subways or buses, trains, those types of infrastructures. So when you take a train or a subway or a bus, it might take you to a particular place within a city, but maybe the actual destination where you're trying to go to. So you're trying to go to a friend's home or to a business, to a park. There might be some distance from where the bus lets you off to where you actually want to go, and that's where the private sector might help you actually get that last little mile. So maybe you take a taxi or a tuk-tuk, or you can even just take a bicycle or walk. So we like this analogy because the Agile Biofoundry doesn't go every single place in biochemical space. But what it does allow a company to do is not to have to reinvent the wheel. So it can get a company fairly close in biochemical space in the organism of their choice, fairly close to where they want to go. But then it's up to the private company to get that last mile. So it's important to point out that the company is choosing where to go. So we as a government are not dictating where people go or who wins and who loses. And also the private sector gets to maintain the very valuable intellectual property in that last mile. So this is kind of how we position ourselves. As the Agile Biofoundry is the dark blue, where we kind of enable the private sector, but the private sector really kind of controls where they want to go and generates all the really valuable intellectual property. So that's kind of one way of showing how we fit in as a public entity. So the way that we kind of operate is kind of around the core engineering biology cycle. So we ourselves, for internal projects, or our collaborators, they could be academic or they could be commercial, would choose the destination. So they choose the target for fermentation, for biomanufacturing. And then you kind of go through the typical design, build, test, learn cycle across all engineering disciplines. So we have core infrastructure around that cycle, and I'll tell you a little bit more about that in the next slide. But it's also important to point out that in addition to just the core engineering capabilities, we also have folks that are helping us with the techno-economic analysis and life cycle analysis. We have a dedicated team for bringing on board new microbial hosts and making the ones that we have on board easier to engineer. We also have capabilities for scaling up our processes. So we don't get to super large fermentations, but we can get up to 1,000 liter fermentations. So that's the kind of scale that we're talking about within our Agile Biofoundry. So speaking of some of our engineering biology infrastructure, I'll be telling you about 3 of the different tools going around the cycle. So as you kind of go around design, we have the automated recommendation tool, ART, which I'll be telling you about. Once we have a design in place, we can use the DIVA platform to have researchers specify their designs for the biological systems, and it kind of crosses the divide between design and build, where it helps our operators, including folks like Garima, who will be presenting next, to actually fabricate those designs. We have tools around validating the constructs that we make. We have some other types of tools that, for example, maybe span the build to test components of the cycle, where you can integrate pathways, expand them in place, and then contract them. And Garima actually had a paper that came out a few years ago that has a related technique called Piace. So you might want to look into Garima's paper around that, which might be of interest. We have a variety of different types of testing methodologies. We have lots of capabilities around transcriptomics, metabolomics, proteomics, lipidomics. You might have seen in Aindrila's and Deepika's presentation earlier this morning for you around some data that was generated from these types of pipelines, for example. We also have things like biosensors, either in microfluidic types of devices or just using fluorescence activated cell sorting. We have a variety of different systems for storing the data. Lots of the primary experiment data will go into a lab key based database. And then once this is processed and after data quality assessments, then it goes into our experiment data depot, which I'll be telling you about. We also have a variety of different modeling approaches, and this might have been the space when Professor Amit Ghosh was actually working with us at the Joint Bioenergy Institute. This is kind of the sector of the cycle where Amit would have been focusing a lot of his efforts, especially around some of the metabolic modeling and flux balance analysis. We also have a variety of machine learning and artificial intelligence types of approaches, spanning things from Bayesian inference to kinetic learning to deep learning. And then we're back to the beginning of the cycle. So in this talk, I'll really be talking mostly about ART, DIVA, and the experiment data depot. So in terms of ART, so this is the automatic recommendation tool, and it's a machine learning tool that really kind of helps us suggest through predictive modeling where we should be trying to go next in biological space. So the idea is you start with a set of data from things that you've done in the past, which could be stored, for example, in the experiment data depot. You have an objective, so maybe you want to increase the titer of the molecule that you're attempting to biomanufacture, and then ART will generate a series of designs. So it does this through combinations of machine learning, Bayesian ensemble modeling, parallel tempering for global optimization, and the output is going to be a series of probabilistic characterizations of predictions. Now, after ART, we'll maybe see a little bit of DIVA. So DIVA stands for the Design, Implementation, and Validation Automation Platform. So it really kind of spans the design to build sectors of the cycle. And as Professor Amit was describing, this might be a platform that he himself has used before and continues to use. So I'll probably be showing you a little bit around of the DIVA platform. And the third platform that I'll be showing will be the Experiment Data Depot. And this is where we take some primary experiment data in LabKey, for example. These might be some of the omics data sets, or things like just high performance or high pressure liquid chromatography, sequencing data for things like transcriptomics. It could just be LCMS, again, for some metabolites. It could be small scale fermentations using a bioelector system, or even just really simple types of shake flask or multi-well plate types of data sets coming in from plate readers. Now you feed all of this information into the Experiment Data Depot, and this is, it'll give you some very kind of simple visualization tools of the data, so you can just have a sanity check when you see the data. But the really important thing is that since the Experiment Data Depot really structures and standardizes the formatting of all of this data, the folks in data science and modeling working downstream have a very easy time accessing the data because it's always structured in a standardized way. So they don't have to spend a lot of their time trying to convert formats of Excel and so on. So this really enables the downstream learn folks to do their jobs better. And we're constantly working on making the Experiment Data Depot easier to use, so better routes for importing data, and making it faster so it can support larger data sets and make export times shorter. So in terms of where we're going to be going with these tools, so one thing that I'll show you in a few minutes, I think, will be the web interface for art. So this really kind of enables people that don't necessarily program in Python or use Jupyter Notebooks to access a limited subset of the functionality of art, and that's kind of what I'll be showing you. But lots of people actually can use art, and it's been published, and I'll show you the link to the paper. But it's really available now as academics. You can get access to the source code, so you could run it on the command line. There are Docker containers available, and typically people might use it through a Jupyter Notebook, which is also presented in the paper for art. So some of these things have already been accomplished with the publication of art, and there's some other things that we're going to be trying to use art for. So these would be trying to go after more discrete or categorical input variables. So instead of learning over more continuous variables like protein concentrations or metabolite concentrations, you could learn over, for example, gene orthologs, gene copy number, things that are more discrete in nature rather than continuous. Making some of the objective functions more sophisticated and starting to apply some of these predictions, for example, to optimizing fermentation media. We often will look at a corn stover derived feedstock that has been deacetylated and mechanically refined and then enzymatically hydrolyzed. And one particular project in general in Agile Biofoundry that we've been working on is looking at the production of fatty alcohols in Ralstonia toroides, which is an oleaginous yeast. And you can do these through iterative cycles where over time your models get better and better. So you might see your kind of the distributions of probabilities getting tighter. So you have kind of tighter confidence intervals. And it also will predict a number of different types of strains. So hopefully we'll see a taste of that during the software presentations. In terms of DIVA, we have stood up a public server. Well, I'll be showing you, I think, the instances probably from the Joint Bioenergy Institute, which everybody can sign up for with just an email and some basic information. We also have the counterparts for the Agile Biofoundry, but since the JBay project is a little bit more mature, they have a little bit more data, so it might be a little bit more fun to look at the JBay instances. Kind of like we have for our web of registries, where a number of entities around the world can stand up their own instances of our ICE repository, which I'll also probably be showing you a little bit. We've also been trying to work towards a web of divas, where different institutes across the world can stand up their own instance, and then they can choose to share with other institutes some of their design. So maybe after you publish a paper, you can make that design public within your Diva platform and allow researchers from around the world to actually see what exactly you were doing in your design. We've also been integrating a bit better with some of our biosecurity tools, including the biosecurity list screening software approach. Right. So, and then in terms of the experiment data depot, again, really it's maybe trying to add some additional types of workflows and data sets, including more support for example, around our bioreactor types of data and workflows, and just continuous improvement and making things better and easier for people. So before I actually try to show you some of the software here in a live demo, maybe just go ahead and do my acknowledgements now, and we can come back to this slide at the end of the presentation. But a number of people contributed to the automatic recommendation tool. So Zach really started art, and then Tiana has been continuing to work on it, and she's the lead author on the paper. And then Mark Forward worked on the web user interface. And Hector Garcia Martin is really kind of the principal investigator responsible for art. In terms of Diva and ICE, this has largely been developed over many years by Hector Plahar with some more recent support by Steve Lane. The Experiment Data Depot was really developed by William Morell and Mark Forer with some guidance from Chris Petzold and again Hector Garcia Martin. And the funding for the Agile Biofoundry comes within the United States Department of Energy, within its Energy Efficiency and Renewable Energy Office, within Bioenergy Technologies Office. So the BETO office has really been supporting the vast majority of all the work that I've presented, and Jay Fitzgerald is our technology manager. And then a lot of these tools, or actually all the tools shown on the screen, were initially developed at the Joint Bioenergy Institute under support from the U.S. Department of Energy, but now within the Office of Science, within the Biological and Environmental Research Office, and JBay is one of the 4 bioenergy research centers. So I think what I'll probably do now is I will go out of PowerPoint, and maybe what I'll do actually is I'll start with Diva. So I'll kind of start at the top of that engineering cycle between build and test, or sorry, between design and build, and then I'll go into EDD, and then maybe I'll finish with art. So this is public-diva.jbay.org. So that's kind of the website. Maybe I'll just log out really quickly and just kind of show you. This is going to be the same for most of our tools. If you don't have an account, you could, for example, click on register, and you just enter with your name, email address, and maybe you're at IIT Kharagpur or whichever institution you belong to, and then you can just register. So these tools are accessible to everybody that's watching this presentation. But maybe I'll just log in. And Diva, when you pretty much log in, you see a dashboard of maybe some of the constructs that are in construction, designs that you've recently viewed, maybe projects you've recently viewed, kind of like a histogram of constructs as they've been created, and then an activity feed. So maybe to kind of just give you a flavor for what this kind of looks like, let's go ahead to designs, and maybe I can just open up like a built-in example design to kind of give you a flavor for what these tools look like. So this is a given design, and we do have a kind of like a visual editor. So this is going to be a design for a combinatorial library of plasmid DNA. So here, left to right is really 5' to 3'. and then top to bottom are different combinatorial variants. So in this particular design, we have a vector backbone, and then we basically have a single version of GFP, but just upstream of GFP, we have 2 different signal peptides and 2 different glycine linkers. And then downstream of GFP, we have 2 different degradation tags. So we would have 2 times 2 times 2, or 8 different combinations of constructs. So this is pretty much where people would go in and they would specify their sequences. And then this would be tied, and I can show you this in a little bit, would be tied together with our ICE repository of DNA sequences. So if you go to any one of these particular parts, for example, basically behind all of these is a source plasmid. So maybe this backbone is every part of this plasmid with the exception of GFP-UV, and it starts at a particular place and it ends at a particular place. So what we can do is we can preview these different constructs. So again, we should have 2 times 2 times 2, or 8 different plasmids. So if we just kind of preview what these would look like, would we need to build them? Here's our plasmids 1 through 8. And you can kind of just page through these different constructs, and you have a quick literal visualization. And the only thing that's really changing here would be the degradation tag and the signal peptide. So maybe as we kind of go, maybe it goes from the BMC signal peptide, and now we have the CCMN signal peptide, and so on. If you want to see at the DNA level, you can see that. Or if it's helpful, you can actually try to visualize both side by side. So maybe if you just want to kind of see the DNA next to where the actual plasmid map is, you can do that. And then in terms of getting actual help as going into the build process, we support a variety of different types of DNA assembly methodologies. So you can do, for example, a flanking homology style method, like a Chewback method, or yeast assembly. You can also do type 2S methods, like a Golden Gate type of a method. So if we actually run this type of approach, it will actually design all of our primers for PCR and design all of the overhangs for the Golden Gate assembly, etc. And this is what our DIVA team uses then to actually fabricate the plasmid. So this might be a routine thing that Garima uses in the course of her work. Right. So the other thing maybe to see is we can look at maybe some things that are finished. Let's see if we can do that. I want my designs, I want all designs. There we go. So maybe what we can do is we can just click on a particular design that's kind of gone through the fabrication process, and you can kind of just get a flavor for what the system does. So there was a researcher in Colorado in the US that we're collaborating with, so Xiang Gao, and Gao is the one that designed the design. And then in our DIVA team, one of our coworkers, Garima and I, is Enrique de Paoli, and he basically is the person that's going to be fabricating the design. So he might look at the design and review it and give some suggestions to Xiang to change to make it easier for us to fabricate. And then after everything looks good, then it starts actually going through the build process. So maybe Enrique or one of our other coworkers might order reagents, including primers or synthetic DNA, and then you can kind of step the process as you're going through the build, where you're doing transformation or sequencing clones and eventually shipping it back out to the user. So it's a platform that allows people to kind of collaborate on designs, or having a division of labor where somebody might be more responsible, like Xiang, for the design, and then other people like Enrique might be more responsible for actually doing the fabrication. And you can have also observers like Garima, who can be watching the design, but not necessarily editing the design or making any changes. So that's just kind of a flavor for that. And the other thing that's nice is that after a design goes into construction, it actually gets automatically deposited into our ICE repository. So this is our ICE platform that really manages all of our plasmids and microbial strain information. And again, this is our public website, public-registry.jba.org. So anybody can create an account and use this platform to store all of your own sequences. And it's important to point out that you don't have to publicly share all of your sequences with everybody. You can kind of control who is able to read or who's able to write to your entries, or you can actually make the entries visible to everyone after publication. So we haven't made this particular entry public to everyone yet, but what we typically do, both within the Agile Biofoundry and within JBay, is we do typically after we publish, then we make that particular information public. So this might be a paper that we published in 2014, and all of the plasmid and strain entries associated with this have been made public, so anybody in the world can log in and access this information. So that was a little bit of information about ICE and DIVA. And then if we want to go see the experiment data depot, again, this is public-edd.jbay.org. Anybody can sign in for an account. And this is where we might deposit information that was published. So maybe what I can do is show you one particular data set that we published, and this was a company collaboration with the Ajinomoto. We might have lots of different types of data. So I guess in this experiment, we have gas chromatography mass spec, we have HPLC, we have NIMS, which is almost like a MALDI mass spec approach. We have just regular plate reader data, optical densities off of a multi-well plate, and we have targeted proteomics data. And there's lots of strains associated with the study. And you can look at specific types of data sets. So maybe we only want to look at, for the moment, HPLC data for certain metabolites in a couple of strains. So you can kind of do visualizations and these types of things. You can also export the data as well. So this is just kind of an example of some of the things that you can do. Right, and then I can also show you that if we look at the table, then oops, let me go back to that. Then we should be able to find links to our ICE strain. So let's check that out. So in the experiment description, we have all of these different strains. So if we click on one of these strains, it'll actually take us to our public registry where it stores information about the strain, and maybe this particular strain contains one specific plasmid. So we really try to have each tool in our collection of software platforms responsible for a very specific domain. So the experiment data depot is really responsible for our processed, actionable biological data, but it doesn't have to store all of our information about plasmids and strains because that's all stored in our ICE repository, and they just basically link to each other. So if I look at the strain entry in the registry, we can see there's a link to experiment data. So I can basically follow that link and it'll take me back to the experiment data depot. So these tools kind of cross-reference and link to each other. So that's basically the way that those types of tools work. And Professor Ghosh, I know that I'm a little bit over time, but we've already worked it out with Garima. So I'll probably take just a couple more minutes, and I think Garima will have plenty of time. So don't get nervous if I'm going over by a little bit. I think that should be fine. All right, so now we've kind of seen the experiment data depot. We've seen ICE. We've seen DIVA. Maybe what we can do now is to go to ART. So let me, sorry, the WebEx thing keeps getting in my way, so I'm a little bit slower than normal, but let's go to art.agilebiofoundry.org. And this particular web user interface hasn't been published yet. But it is going to be getting published soon, so I'll just kind of give you a preview for what it looks like. But it's active now, so if you all wanted to actually log in and try it, it's just at art.agilebiofoundry.org. And I think what I'm going to do is I'm going to just show you kind of like what the example input would be and what the representative output would be. So it might be hard for you all to see. Let me get the screen a little bit bigger. So this is just maybe like the past experiments that we've done with a couple of different strains. So each one of these strains is not very, it's not described in a lot of detail, but we're just calling it strains 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All the way it looks like we have something like, it looks like we have something like 90 data points. So if we have, let's see, we have something like how many different proteins? So it looks like we have 8 different proteins that we're measuring, and then one measurement of the production. And this is just kind of mock data to kind of give you a flavor for how it would look. This isn't real data, but just to kind of give you a flavor for the type of data that you would use to train ART. So what you can do is you can just take that Excel sheet or a comma separated value file, and you upload it, and it can give us warnings like maybe we don't have a time series of data, so Art's going to assume that all of the data is coming from a single time point. And then what we really just need to do is tell it, okay, what are the things that we're measuring as input variables, and what is our response variable? So our, let's see here. Basically everything other than production is going to be an input variable, and then production is going to be a response variable. And we can do something like we really want to maximize production, which is our response variable. And then we're going to ask it to give us 16 different strain recommendations. So 16 different levels of proteins to hopefully try to help us maximize production. So we'll click start. And it does take a few minutes, so I'm just going to submit the job, and basically it'll email me when it's done. But I have some previous results loaded that we can end up seeing. So it does have a couple of quick little visualizations. So maybe you can have some interesting visualizations, like if you want to achieve a certain probability of achieving that production increase, how many different strains would you need to make? Now, we basically said that we would be asking for 16 different strains. So here's 15, so 16 is probably the very right end. And it's saying that based on what its probabilistic model suggests, we should be very confident that we're going to be able to hit, if we build all 16 strains, that we should be able to accomplish that increase in production. So there's other types of visualizations that it'll generate. So here's our 16 strains to be produced. And then here is kind of the distribution of production. So maybe right now, our baseline production that we already have might be, say, around like 0.57 or something like that. So there's a probability for any one of these strain recommendations that it actually has worse production, but there's also a probability that it has more production. So if you make enough of these and they're independent enough, then you're probably going to get one of the 16 to have a higher level of production. So that's kind of the nice part about the predictive models that are probabilistic. And then here's pretty much like how we see our historical data versus what the model is predicting. So we actually see a pretty good linear fit between our previous observations and what we're actually predicting using the model. So that's nice to see. And then we'll just give you a spreadsheet with the actual recommendations of the different types of levels for each of the proteins. So that's just kind of an example. All right, so maybe what I'll just go ahead and do, maybe I'll just go back to my slides. And just as kind of like a summary slide, maybe I can just kind of go back here for a moment, and then I can go to the acknowledgement slides. So I guess I told you a little bit during this presentation about the automatic recommendation tool, DIVA, and EDD. We also touched briefly, at least in the software demos, around our ICE registry platform. All of these tools are published. Oh, one thing I said that I was going to do that I didn't do that I can go back to in a second is ART is now published. DIVA hasn't been published. but we're going to be writing a manuscript for that soon. And the ICE registry and EDD have also been published. So maybe if you're interested in the papers, for example, so this is again art.agilebiofoundry.org. There is a link to the art publication. So this is a paper that we submitted to the bioarchive, but even more recently, it's been published in Nature Communications. So you can just copy and paste the title and find the automated recommendation tool in Nature Communications, so you can read more about that. And then we were also looking at public EDD, and I believe there should also be a link here at the top to the EDD publication. So if you want to learn more about the EDD, it's available as well. So yeah, so publications are available too. So I think what I'll just do is go ahead and leave it on the acknowledgement slide for the moment. And Professor Amit Ghosh, if you want to take any Q&A, I think we should have a few minutes for that, and then we can give Garima maybe 15 or so minutes, and I think that should be good for her. So thank you very much for your attention, and thank you for the opportunity to present.
Thank you, Dr. Nathan Hillson. It was a very interesting talk. As I told you that I have used many of these tools before and really benefited where I can design my own spine and use it. The new thing I got is the art, that is the automation recommendation tool, which is even better. I think students and who are listening now, they can use all of it and they can bring a huge change in their research career. So right now we don't have much time for the questions, so I'll just directly head toward the next speaker. So thank you, Nathan. You came up in the early morning, and this is really an innovative talk, and we really hope to get new things from you when you come in person next year. So hopefully you can come next year and visit us. We'll have more personal interaction and get benefited. Thank you, Nathan. Thank you for joining us.
Yes, Dr. Hillson, I'm also just welcoming you to Kharagpur, and my open invitation to you. So because of Corona, we could not get you this time here, but we are expecting you at any point of time. So whenever the situation is a little bit getting improved, we will be expecting you, and my open invitation is there for that.
That's great. Thank you very much for the invitation, and I look forward to visiting you all. So thank you very much.
Thank you, and thank you for your excellent talk. So thank you very much.
Thank you.
So our next talk of the workshop, this is the last talk, which will be given by Ms. Garima Goel from Joint Bioenergy Institute, Lawrence Berkeley National Lab, Berkeley, California. She will be talking about fatty acid biosynthesis, that is inducible and orthogonal. So I request Garima to start her talk. You can start your presentation. Thank you.
And Garima, is your audio working?
Can you hear me now? Hello?
We can hear you. Yeah, we can hear you. Yeah.
Yeah, I think I'm not able to share my screen. Just give me a second.
Okay. As a fallback, if you want to email me your slides, I can present as a fallback.
Okay, let's do that. I'm going to email you my slides.
Okay. Sorry for the delay, but we'll get going very quickly.
No problem. We have time.
Sorry, guys. Taking a bit longer. Then I just sent you the email.
Okay, I'll look for it, and as soon as I have it, I'll share my screen.
All right,
So,
thank you.
Grima, yeah, you can go ahead and get started, and just tell me to go to the next slide.
Okay. Sorry for the technical glitch, guys. My name is Garima. I am a principal research associate at Joint Bioenergy Institute. I am also pursuing a PhD from TU Darmstadt, Germany. Today, the topic of my presentation is fatty acid biosynthesis, inducible and orthogonal. Next slide, please. So, engineering heterologous fatty acid metabolic pathways to produce biofuels and other bioproducts is complicated. It is made much more difficult by concurrent and highly regulated native fatty acid metabolism. Genes belonging to this pathway are essential for
Did we lose Grima? Amit?
We lost it. No problem.
It looks like she's still connected, but I can't hear her.
No problem. We'll wait.
Okay.
Hello, can you hear me?
We can. Yeah, you can restart.
Okay, I'm really sorry about that. So I'm going to restart my presentation. So engineering heterologous fatty acid metabolic pathways to produce biofuels and other byproducts is complicated. It is made much more difficult by concurrent and highly regulated native fatty acid metabolism. Genes belonging to this pathway are essential for cellular growth and are distributed across the genome, which is why it is almost impossible to remove them wholesale or repress them in a controllable manner. Next, please. So genes for metabolic pathways or physiological capabilities are often not natively co-located in the genome. The approach is to remove them from the genome and put them in a replicating bacterial artificial chromosome that can be degraded controllably later on. Additionally, modules for heterologous pathways can be supplemented on back plasmids too. In this approach, there are three major points. One, native pathways are deleted from the genome. Two, back-based modules for native and non-native metabolic pathways or physiological capabilities are created. Three, these back modules containing pathways can be conditionally expressed or repressed, which lead to decouple the fatty acid biosynthesis from cell growth, self-regulation, and consumption of fatty acids for other biomolecules. Next, please. Particularly in Fabio, which is conceptualized by Nathan and another scientist at LBNL, Harry, we are not deleting the entire fatty acid pathway from the genome. Instead, we are focusing on highly regulated genes responsible for certain physiological capabilities. One of the two modules, BAC-A, or also called FAS-A, has genes from native fatty acid biosynthesis to support cell growth. It contains ACC plus other fatty acid genes, genes from phospholipid synthesis, lipopolysaccharides, thioesterases, etc., enzyme families. The main features of this module are to retain native gene regulatory components and repress them after the growth phase. All the genes in BAC-A module are deleted from the genome to create a modified host chromosome. FAS-B module's main function is to produce fatty acid precursors. It contains genes from heterologous fatty acid pathway, such as non-native genes like ACC, ACPT, ACPP, FAS1, thioesterases, etc., for enhanced desired product formation, which are uncoupled from growth and acyl ACP regulation. Main features are non-native fatty acid pathway genes, which are inducible during non-growth phase and should make tailored acyl CoAs. Next, please. Some other functionalities of this project are we can show how synthetic biology can enable transformational changes in control over bacterial metabolism for biofuels and products. We are taking advantage of latest assembly and genome editing methodologies such as CRISPR-Cas9. This modular approach will lead to a production-oriented minimal genome, and these modules can work in combination for optimal production of a desired compound without the added strain of maintaining unnecessary genes and proteins. Advanced synthetic biology tools like J5, DIVA, ICE are being used for high throughput automation so that we can do efficient design of experiments and lab work. Next, please. So both of these figures that you see on the screen are idealized representation of Fabio's strategy. Figure on the left is the comparison of an engineered E. coli strain with Fabio's strategy to a non-Fabio engineered strain. After the growth phase ends, strain is triggered to activate Fabio, which results in almost no increase in OD and huge increase in metabolite production as compared to a non-Fabio strain. Figure on the right shows what activating Fabio means. When the growth phase ends, FAS-A module is repressed and FAS-B module is expressed, resulting into glucose conversion to a fatty acid production and not to OD. Next, please. The figure on the right is fatty acid biosynthesis pathway. It's a complex pathway with three main components: initiation from acetyl-CoA, elongation of fatty acid chain from malonyl ACP, and acetyl-CoA. Third is beta oxidation from acyl-CoA to produce metabolites. Without going into too much of details, I just want to point out the genes which we are targeting for BAC-A module and also for deletion from the genome. All the highlighted in pink are the genes, part of various enzyme families, which are known to be highly regulated. Genes from fatty acid initiation and elongation steps, lipopolysaccharides, and other enzyme families. Some of them are known to cause cell death if they are over or underexpressed, such as ACC complex or FAT-D. These are the genes from the initiation step. And for some, we don't even know what the effects are going to be when they are deleted from the genome. Next, please. So selected genes responsible for native metabolism that we just saw in the previous slide are placed under native constitutive promoters on a replicating artificial chromosome, also been calling it BAC, capable of self-destruction or repression with dual origin of replication, CEN-ARS for yeast and OES for E. coli. For each selected gene, target sites adjacent to PAM sequence are designed. These are modified by codon optimization to make them dissimilar so that Cas9 can specifically target the native genes in the genome. Below is the BioCat design for the BAC-A plasmid. Next, please. We are using CRISPR-Cas9 along with lambda-red homologous recombination to delete the genes from the genome to create a modified host chromosome. 3 plasmids are transformed into the host strain. Plasmid 1 is encoding for Cas9. Plasmid 2 is encoding for guide RNA. Guide RNA and Cas9 form a ribonucleoprotein complex which recognizes the target site and introduces a double-stranded cut in the chromosome. Plasmid 3, which is delivering fixing template, this fixing template, along with lambda-red proteins expressed by plasmid 1, repairs the double-stranded break. All 3 plasmids are capable of self-destruction. Plasmid 1 is a heat-sensitive plasmid. Growing the strain at or above 37 will cure this plasmid. Plasmid 2 can be cured by CRISPR-Cas9. Guide RNA for this plasmid can be encoded by plasmid 1 under IPTG inducible promoter. And plasmid 3 is a suicide vector. Next, please. There are 27 genes that need to be deleted from the genome. Certain gene deletions may lead to cell death due to BAC-A complementation failure. Order of gene deletions could play a very important role too. For the faster knockout rate using CRISPR-Cas9 and more streamlined process to decide the order of deletion, genes were divided into gene groups and gene clusters. In gene groups, 2 to 3 genes were grouped based on their size and located in BAC-A as well as genome. In gene clusters, genes located adjacent in the genome are clustered together. Now instead of 27, we are only doing 9 deletions to accomplish and determine the order. Next, please. So we first tried parallel approach, where all these 9 groups were attempted to knock out the genes in parallel. In this approach, we want to establish which gene groups and clusters would be problematic when we attempt to knock them out from the genome. And second, to determine the order to carry out the knockout for modifying the genome. Next, please. Yeah. So we got most of the genes responding well to the CRISPR-Cas9 and gene grouping approach. 2 of them didn't work, which could be because of various factors. One of them has genes from ACC complex, which are known to have detrimental effect if they are removed from the genome. Second could be CRISPR-Cas9 failure, because an attempt to remove 5 kb DNA fragment from the genome was made. Next, please. So as the name suggests, the next is carrying out these 9 deletions in a sequence so that we can achieve a final modified genome free from the selected growth essential fatty acid genes. Order for the deletion is determined following the results from parallel gene knockout approach and trial and error in sequential approach. Can you click next? As can be seen, order is modified from the proposed order. There are multiple strains with different sets of gene deletions. If all gene deletions are not achieved, we're going to have a library of strains that can be tested to see which one provides the best support for the cell growth. Next, please. So just to quickly go over the experimental protocol, there are 4 steps in Fabio gene knockout workflow. An engineered E. coli, an existing JB strain, is transformed with BAC-A plasmid that becomes the base strain for mutagenesis. Step 1 is transformation of the heat-sensitive plasmid 1. This plasmid has 3 main functions. It is encoding for Cas9 constitutively. It is encoding for lambda-red proteins induced by arabinose. It's encoding for guide RNA targeting thin CRISPRs induced by IPTG. Step 2 is preparing fresh electrocompetent cells and transforming thin CRISPRs and fixing templates to knock out the target genes. Step 3 is confirming the deletions via calling PCR and MiSeq sequencing. And step 4 is curing the thin CRISPR plasmids and getting ready for another round of deletion. Step 2 to 4 can be repeated n times until all the deletions are performed. Next, please. So in conclusion, so this is in alignment with JB mission, alongside an applied objective to engineer E. coli for efficient fatty acid-derived biofuels and bioproducts. It is also likely to provide deeper understanding of a process, fatty acid biosynthesis, that is fundamental throughout the bacteria and eukarya domains. We are introducing 2 orthogonal fatty acid biosynthesis pathways in E. coli. Phase A to carry out native function essential for growth. Phase A design and construction is complete. Phase B to catalyze the production of desired biofuel precursors. A key goal in design of Phase B is to decouple fatty acid biosynthesis in the system from cell growth, self-regulation, and consumption of fatty acids for other biomolecules, such as phospholipids and lipopolysaccharides. The Phase-B system allows us to have more control over fatty acid properties, for example, chain length, unsaturation, branching, so that we can modulate the fuel properties of fatty acid-derived products. Next, please. So all these people helped me in this project. A special thank to Mason for providing guidance at various stages of this project. And thank you all for listening, and thank you for inviting me to present in this Spark workshop. Thank you. I'm happy to take any questions.
Thank you very much. Very interesting talk where you have modified so many genes all at one time, one transformation, right? So this is really motivating work, and it will improve it will decrease the time of transformation, and also you are removing the CRISPR plasmid using another plasmid. So this is really a noble type of techniques you are using, which will help the community. So for deleting the gene, are you using any donation or how you are deleting 9 genes together? So
I am deleting them in a sequence. So I made 9 different plasmids. all these 9 different, or syn CRISPRs, all these 9 different syn CRISPRs have different number of genes from 1 to 2 to 3, and they are being deleted in sequence. First approach is to try them in a parallel, and depending on the results of those parallel deletions, as I was showing, then the sequential gene deletion is carried out, where one at a time, one syn CRISPR is deleted at a time.
This is in a single transformation.
It is, I'm sorry, what?
In a single transformation you are doing.
It's electrocompetent cells, so electrotransformation. Is that what electroporation?
So Grima, I think what Amit was asking is if you basically do sequential transformations and deletions as opposed to doing 9 at the same time.
So I have tried. I think deleting more than 3 genes is too much of cell burden for E. coli. So there is a limit of how many genes can be deleted from the cell genome. And I am trying to push the limits with deleting as much as possible. So if I guess if I'm understanding the question right, deleting all of the 9 syn CRISPRs at one time hasn't been possible for me. So I'm trying one syn CRISPR at one time and.
Okay. Yeah, very interesting. Thank you very much. Really appreciate your work and hope to meet you next time when we have the next workshop. So I invite Nathan and Garima to actually visit our institute anytime next year when we have the next. We have one more meeting. We have for this project. Hope we meet in person in next year and things become normal.
Yeah, thank you very much.
Thank you, Nathan. Thank you very much.
Thank you. Yeah, thank you, Amit. Thank you. And thank you for organizing it.
Thank you so much. So with this talk, we are ending this workshop. We are end of the workshop. So hope you. Hello. Anybody is. If there is no more question, then we thank Garima and hope to meet next time when we get the situation better. And with this talk, we are ending the workshop. Hope you enjoy the talks which are happening for last 12 hours. And hope to meet you next time when we organize another workshop. We can meet in person and get more interaction in the future. Thank you. Thank you so much. Thank you. Bye. Bye, Nathan. Have a nice day. And Garima, have a nice day. I see you soon.
Have a nice evening. Bye.
Bye. Bye.